In this section, we're going to talk about convex optimization problems, and we'll start in detail. We'll start by talking about what's an optimization problem. We'll talk about what are the parts in an optimization problem, how do you define one. We'll get quickly to what's a convex optimization problem. We'll talk about quasi-convex optimization. And then for a while, we're going to look at just common families of optimization problems, linear programming, quadratic programming, something called geometric programming. Then we'll look at generalized inequality constraints, and the most famous of these is semi-definite programming. And finally, we'll look at the idea of vector optimization. That's when your objective function is actually a vector and not a scalar. Okay, so let's start. What's an optimization problem? Well, an optimization problem is something, it's described and written this way. It says minimize f0 of x, that is the objective function. X is a vector in Rn, that's called the optimization variable, or another name for it, which is a great name, is the decision variable. That's wonderful because it kind of tells you that's what you have to decide. So f0 of x is the objective. Here, you're being told minimize. What that means, of course, is that the smaller f0 of x is, the happier you are. That defines what it means to be better. And then there are constraints. This says subject to, and you have inequality constraints. These are of the form fi of x is less than 0, and there's m of these. And there are equality constraints, also subject to hi of x is equal to 0, and there are p of these. So here, f0 is the objective or cost function. Fi, these are called the inequality constraint functions. And hi are equality constraint functions. And although we'll see many, many examples, I can say a little bit about where some of these things come up. Usually f0 is an objective or a cost. And in any case, it's something that you want to make small, and you're happier the smaller it is. The inequality constraint functions fi, often these will have to do with something like a resource limit. And so this will tell you something about a resource limit, or really how much under the resource limit you are, the capacity. And what this is usually has the interpretation of don't violate a resource limit. Hi of x, equality constraints tend to be, again, we'll see tons of examples, but these might arise in things like balance, that one thing has to balance another. For example, a market has to clear. That means that the total amount sold has to match the total amount that's being bought, something like that, right? So that's where you would get these. We'll see lots of examples. I should mention one thing. That is that you can also maximize a function, in which case it's not called a cost function. If you maximize an objective function, the objective function is often called a utility. That's one name for it. But it could also be something much more specific like profit or something like that, or some other quantity that's obviously good depending on the application, right? And entire fields will use preferentially either minimizing a cost or maximizing a utility or profit or something like that, right? So, and you can joke about what that means about the people in those fields and like, what their psychological makeup is or something. It's not a big deal because if you wanted to maximize a utility, we could minimize negative utility. And it's useful to have a standard. Our standard will be minimize because we'll have a lot of equations that later involve constructs that involve a minimization, and you have to turn them around in your head when you're maximizing, and then you get a headache. So it's easier just to have a fixed, clear version of it. Okay. Now, the set of x for which fi of x is less than or equal to 0 for all of them, and for which hi of x is equal to 0 for all of them, such points are called feasible. That's called the feasible set. And on the feasible set, you evaluate the objective. This is a set of numbers, right? It's the objective values for all x which are feasible, and the infimum of that set of numbers, that's like the minimum, that's called p star, and that's the optimal value of this optimization problem. Okay. Oh, so for people who haven't seen it, you can read inf as min. Min is a completely standard function, and it means only one thing. It has no other meaning in mathematics. That meaning is this. It takes as argument a finite set of real numbers, period. And it returns the smallest of them, period. There's no other definition of min. Inf is, in fact, something like min generalized to infinite sets. It's something like it's the greatest lower bound, people say. It's the largest number that's smaller than all the numbers in the set. And an example would be the inf of 0, 1 is 0, for example. So you would not write the min, except very informally. Okay, I should make it, let's see, a couple more comments I wanted to make. Oh, one is this. It is absolutely standard that the inf of the empty set is plus infinity. Again, there is no variation in that. That's always the case. And if you do that, various rules about infimum hold in this case. And if a set is unbounded below, that means that, for example, here there are x's which satisfy all the constraints, but for which f0 of x can be made as negative as you like, right? Then you would say the problem is unbounded below, and we would simply say p star is minus infinity, right? So that's the idea. I mean, from an optimization point of view, I guess that's the best thing that can ever possibly happen, although what it really suggests is that your model is wrong. It hasn't been set up correctly or something like that. By the way, this has got a very amusing name in some cases, right? There's at least one case I know where when p star is minus infinity, it's referred to as euphoric breakdown, which I think is just a great term for it. It means that you can be as happy as you like. Anyway, I won't go on, right? That's p star is infinity. Okay. So this is an optimization problem in standard form. Oh, and I want to say one more thing. Never confuse the mathematical operator min, which is a function that takes as argument a finite set of real numbers and returns the minimum, and this word minimize. They are absolutely different, although some people kind of use the same word for it. I don't approve of that. It's not so bad as long as they know what they're doing, but they're different. Minimize is not min. So min is a function that takes something like this, right? 0, minus 1, 2, right? And it gives you minus 1. There's a function, okay? Minimize you should think of as something that is part of an optimization problem. And the way I think of this optimization problem, it is not a number. This is a number. This is not a number. This is an object. It's an optimization problem object. If you like to think of this in terms of like object-oriented programming, that's an object. Minimize is a key word that introduces an attribute of an optimization object. That's what it is. So this is saying that problem, dot objective is f0. That's what it's saying. Subject to, again, is something that's a key word that tells you that what follows that is a set of constraints for that problem, okay? And so you would never say this optimization problem is 3. What you can say is that its optimal value is 3. That makes sense. Okay. So we should talk about the idea of an optimal and locally optimal point. You say x is feasible if you're in the domain of the objective and you satisfy all the constraints. Now that implies you're in the domain of all the constraint functions, right? And a feasible x is optimal if its objective value is equal to the optimal value of the problem. Okay, so that means, well, just what it says. It means that x gets an objective value that is as good as the least possible value among all other feasible points, right? And we'll let x opt be the set of optimal points. The x opt can be empty. In other words, there is no optimal point. It could have a single entry. It could be a singleton. There's a unique optimal point. And it could actually be a set with 2, 3 points, finite number of points, or it could be a set with an infinite number of points, right? So in convex optimization, the second one can't happen. Well, sorry, the third one. If you have 2 points, then for a convex problem, which we'll talk about shortly, it means that you have an infinite number. So, but we'll talk about that in a bit. Okay. Now, locally optimal is a point which has the following property. It says that there's a positive r such that if I add the constraint that you are no farther than r away from x, so x is the point that we're going to certify as locally optimal, then x really is optimal for this problem, something like that. So that's what that means. So let's see what that means. Here, let's draw a function. Looks like this. Well, in fact, our function will be this one, x cubed minus 3x. That looks like this. It's got it at plus 1. It's here, and sorry, that's at minus 1, right? And at plus 1, it's got a local minimum. And the claim is that this is a local minimum because if I were to add the constraint that you're between here and here, then for sure that value is, that's x equals 1, is the optimal point for that problem. Okay. Let's look at some simple examples. So first it says let's minimize 1 over x. And here x has to be positive, right? That's because that's the domain. That's the declaration of the domain of f0. And in this case, there's no optimal point, right? Because we go something like this, right? Here's x. And the point is that the larger x is, the smaller 1 over x is. And you can make this number as small as you like. You cannot make it 0. You want to say, you would like to make it 0 by saying x equals infinity, but that's not allowed. So the infimum of these points is 0, okay? But there is no point x for which 1 over x is 0. So this thing has no optimal point, okay? Another one would be minus log x. So minus log x would look, something like this, but it would come down at 0. At 1, it would go through the value 0, and then it would keep going down very slowly, but it keeps going down. And it goes down as low as you like. That says p star is minus infinity, because the infimum of all these points, you just take x again as big as you like. Next example is going to be x log x, negative entropy. So for negative entropy, here, I'll draw that. The negative entropy function looks like this. It goes up like that, right? So for this function, and the domain is all positive numbers here, this really, really does have an optimal value. It's achieved at sort of 1 over e, the value 1 over e, and the value is minus 1 over e right there, right? So this is an example of a problem where these first two are pathologies of different kinds, and this one is the first one where you'd say it sort of has a non-pathological answer, right? So it says if you wanted to minimize negative entropy, or we could say if you want to maximize entropy, you would take x equals 1 over e as optimal, right? Oh, I should say this log, of course, is log base e, right? Not log base 2. Okay, this example we've already seen. This is the one where it goes up and then down and then up again. That's a locally optimal point, but p star is minus infinity. One thing that will come up at various times in the course is this idea of implicit versus explicit constraints. So implicit constraints are the constraints, we don't really say this, but the domain of a problem is the intersections of the domains of all of the fi, including 0, that's the objective function, and all the constraint functions, and all the equality constraints. And so we'll call that the domain of the problem. And what it means is that if you propose an x that's outside the domain of the problem, it means it's inappropriate, because what it means is if you're outside the domain of the objective, it says I can't even evaluate the objective to tell you whether or not it's good or bad, right? So now when f0 is convex and we use infinite valued extensions, there's a seamless way to handle this, and what we do is we simply say we return plus infinity for being outside the domain. That works just fine. In the general case, though, you might return a token that says something like out of domain. Okay. Now, on the other hand, these are explicit constraints, right? So it says these constraints, when you actually say, for example, f1 of x has to be less than or equal to 2, that's an explicit constraint. It says, please evaluate f1, and then compare that number to zero. To compare it to zero. If you're less than or equal to zero, it's just fine. If you're above zero, it's completely unacceptable, right? So, by the way, there's a subtle difference here, and probably this is not a bad way to think of it. There's actually quite a different thing. It's two different types of bad things happen if you propose in an optimization problem a point which is out of the domain of the problem versus one that is infeasible, right? So in one sense, I would say that the first one is a little bit worse. I mean, practically they're the same thing. So if you propose an x and it's just like and what's returned is a message that says this x, I can't even evaluate the constraint number 3. I don't even get a number, right? I get something like a NaN, an NaN, which is not a number, right? So then you can't compare that to 0 or something like that. And so that's sort of, in some sense, that's worse. Maybe this is subjective, but that's worse than actually having F3, having all the functions evaluate, and then having one of the inequality constraint functions be positive. So, okay. Now, a problem is unconstrained if it has no explicit constraints. It does not mean, I mean, you can have implicit constraints. Here's an example of a function like that, or of an example, is minimize f0 of x subject to, minimize f0 of x, which is the sum of minus log bi minus ai transpose x. Okay, so here's just one f0. There are no fi's, none, no hi's. And so here, there are implicit constraints that the arguments to the log have to be positive, right? So you have to have bi strictly bigger than ai transpose x. If it's equal to 0 or worse, negative, you're just out of the domain in log. If you're using the extended value extensions and everything's implemented correctly, and you evaluate something where this evaluates out to minus 0.2, then it might just correctly return plus infinity for minus log of that term. Right, so that's an example. Okay. So a feasibility problem is it's a simplified one, and it's sometimes written this way. You'd say find x, and then subject to a set of inequality constraints. Inequality and equality as well. And these are both optional. Well, I guess we can have a short discussion about unconstrained feasibility problems, right? So those are very easy because any x is optimal. Okay, so this is a feasibility problem, and actually it fits in the general framework in a very simple way because it's exactly the same as the general problem where you minimize an objective that's just identically 0. It just works. Everything, the semantics just works perfectly. Because here's what happens. If you have a point that is feasible for the feasibility, I mean, if it satisfies the constraints, right, then, well, the objective function is 0, right? And so if this problem is feasible, the set of feasible points will be non-empty, and that means there'll be a point whose objective value is 0. If you're feasible, the only objective value you can have is 0, so it's optimal. So any point that's feasible is optimal. And the converse is very simple. If this is infeasible, it says that there's no point that satisfies all the constraints, right? Therefore, the optimal value of this is defined to be the infimum of the function which always returns 0 over the empty set. And that happens to be plus infinity by convention. I mean, it looks strange, but it actually all just works fine. Okay, so finally we get to the formal definition of a convex optimization problem. So that's something like this. It says it's an optimization problem, but so it inherits everything from an optimization problem, all the notions that you have there, like feasibility, optimality, and everything else. But there are some constraints. The constraints are this. The objective function and all inequality constraints have to be convex functions, right? So that's the requirement that's one requirement. And the equality constraint functions must be affine, right? So it's normal for people to write it this way, but if you like, you could write this as AI transpose x minus bi. You would define this to be gi of x, and that's equal to 0, something like that, okay? And so that's your this would be, you'd define these functions this way. But it's more common to write it that way. Okay? And if F0 is if the objective is quasi-convex, then the problem is called a quasi-convex optimization problem. Now, the equality constraints here, which have to be linear, well, which is kind of informal speech for affine, right? Because there's a lot of situations where you talk about linear equalities, and what you really mean are affine equalities. But people have been calling them linear equalities for hundreds of years, so we'll stick with that. In that case, it's typical to collect those into a matrix, right? So that AX equals B, each row is one equality constraint in the problem written out with the equality constraints listed out separately, right? So, okay. And people would call this something, I mean, you might call it a vector equality constraint. It doesn't matter. Okay. Now, one very important property here is that the feasible set of a convex optimization problem is convex. So, in fact, is the optimal set, right? So, and that's very easy to see. The feasible set is simply the set of x that satisfy AX equals B, and then Fi of x is less than or equal to 0. And that's going to be a convex set. Actually, it's very easy to show it directly, but you know it anyway. It's a sublevel set of convex sets, and it's an intersection of, that's an affine set, the set of feasible points for AX equals B, and for each of the convex functions here, it's a sublevel set, which is convex. And therefore, it's an intersection of m convex sets, m plus 1. M sublevel sets and one affine set defined by the equality constraints. Okay. So let's look at an example. And actually, it's meant to bring out a very important point. And that is that convexity is an attribute of the description of the problem. So this is actually very important. It is not. So there's a more abstract definition of convex optimization, which is a convex optimization problem is a problem where you minimize a convex function over a convex set, right? We'll see that this is one, this example, but it is not a convex optimization problem by our stricter definition. It depends on the description. So here, let's look at the problem. It says minimize, it's a problem with two variables. It says minimize the sum of the two squares. You know what the objective function looks like. It's a bowl, right? So it kind of goes up. It says minimize the norm of x or norm squared of x. Subject to, the first constraint says f1 of x, that's going to be x1 over 1 plus x squared, that's less than or equal to 0. Well, it doesn't take long for you to figure out that's not a convex function of x1 and x2. It just isn't. Okay? And the last equality constraint is this. It says x1 plus x2 squared is 0. Well, x1 plus x2 quantity squared is definitely not a convex function. But you look at it carefully, and you realize that these two constraints define a convex set. Why? Because to say x1 plus x2 squared is 0 is the same as saying x1 plus x2 is 0. So that's a line, right? This constraint, x1 over 1 plus x2 squared less than or equal to 0, this thing is positive. So you just get rid of it. It says x1 less than or equal to 0, right? So in fact, the feasible set is array. It's just array, and it's perfectly convex. So this problem is minimizing a convex function over a convex set. But it is not a convex problem by our strict definition, right? So our strict definition is extremely simple. It's basically problem.objective.is convex. You call that method. And if it's not, then it's end of story, right? After that, you iterate over the constraints and you check if every inequality constraint function is convex. And if the answer is no, it's all over. And then you check every equality constraint function, and every single one has to be affine. Okay, so that's our definition. So we would say that this problem is equivalent to this problem. And we're not going to use we're not going to go into a fancy formal definition of what equivalent means, I think, like you would in a CS theory class. Instead, we'll just say, we'll have an informal definition. The informal definition is this, that two problems are equivalent if from one you can readily compute the solution of the other, right? And vice versa, right? So here it's extremely simple, the sense in which this problem is equivalent to that one. Here's the method that does it. You simply copy x. So if you solve this problem, then the solution of that is also a solution of that is a solution of that, and vice versa. If you have a solution of this, it's a solution of that, right? So I guess that satisfies this general idea that it's easy to construct the solution because there's nothing to do. Okay. This problem is convex because the objective is convex function. The constraint, you check the inequality constraint, you look at the left-hand side. The left-hand side is x1. You ask whether the function x1 is convex. It is. Done. You look at the constraint, at the equality constraint function. You ask whether x1 plus x2 is an affine function. It is. Done. So that's a convex. And this will be important, and it'll come up at several points. Okay. Now, here's a very important fact about, and basically elementary fact about convex optimization, and that's this. Any locally optimal point of a convex optimization problem is globally optimal. Right, so it's a very basic fact. It's very easy to show, but it's very important. Actually, it's quite interesting. It says that if you cannot improve, if you find a point where you cannot walk, there's nowhere around you where you can improve over what you have, then you don't have to look farther afield. I mean, that's what this says. And we'll look at the proof, and in fact, I think instead of the proof, I might just draw a picture, and then that'll make everything clear, right? So here's what we're going to do. I'm going to take a point. I'm going to say that x is locally optimal here, and what I'll do is I'll imagine that y is globally optimal. By the way, when you talk about local optimality and you want to make sure you mean just optimality, you say it is globally optimal. So here, I'll say y is globally optimal, and not only that, it beats the local optimum. So this says that there is a locally optimal point x, which is actually beaten by another point. It's that simple. And what I'm going to do is draw the line segment leading from x to y. And we'll look at a point that goes on that line segment here, right? So if I take theta equals 0, I start at x, and as theta goes up to 1, I approach y. And what I'll do is I'll take the, I should mention something. Both x and y are feasible for the convex optimization problem. This z is a convex combination, therefore it's feasible. So that there's no doubt about feasibility. So we only have to worry about the objective function. So let's look at the objective function. Let's just plot f0 as a function of theta. Well, it's going to look like this. Here's theta equals 0. Here's theta equals 1. When theta equals 0, I'm going to plot f of z, and z in turn depends on theta. So if I take 0, then that corresponds to z equals x, and I get some f of x. So there we go. That's f0 of x here. Okay? Then I look at 1, then z is y. And I take that. And by our assumption here, it's smaller. So this is f0 of y. Okay? But now, let's go back and look at the local optimality of x. That says that there's a little range like that, where in that range, you certainly can't do better than f0 of x because x is locally optimal. So that says that whatever happens here in the function, it has to be above that little horizontal segment. Okay? So that's the idea. So now we got a problem, and it's just a geometric problem. I mean, you could work, the proof is 3 lines algebraically, but the picture is actually maybe better. The problem is this. f0 restricted to the line segment between x and z, that's a convex function of theta. And now we got a little problem because we have a convex function of theta that starts out flat but somehow ends up lower. And all I'll say is you can't do that. And your eyeball tells you that. I mean, the algebra, if you could work it out algebraically, it's 3 lines and there's an inequality and stuff like that, but this is clear. So at some point, there's no way a convex function can start out flat and then end up down here. Just can't do it. So, okay. So that's my picture proof of this. Okay. Now we can work out the optimality criterion for a differentiable function. This is useful. It's a good way to start. Later in the class, when we talk about duality, we will work out optimality conditions for full general case with all the constraints, everything. But for now, what we're going to do is we're going to just work out some very simple ones, actually based on an inequality we have for differentiable functions. And it's this. A point x is optimal. This is for the special case of the objective being differentiable. Okay, so it says if the following is true, the gradient of f0 of x is transpose times y minus x is bigger than 0 for all feasible y. Right, so that's the condition. And a picture would look something like this. This dark set, this is the feasible set. Okay, and these dashed lines here, those are the level sets of f. Right, so this is f getting smaller. So as you go down these level sets, that's f getting smaller, and so the semantics of an optimization problem is that you want to move as far as you can, sort of to the smallest level curve of f0 while staying in here. And the optimal point is clearly, it's unique and it's right there, right? One thing you noticed, again, just visually, it's very easy to show even without it, without appealing to any sort of visual stuff, is visually what you see is that in fact the tangent to x is orthogonal to the gradient there, or another, the gradient is an outward normal for x, negative gradient. Okay, and so that's what this says. This says that the gradient at an optimal point here defines a supporting hyperplane to the feasible set at that point, right? So, and there's some special cases we can do. Like, for example, let's do the case where it's unconstrained. So there are no constraints. There's no constraints. So all feasible y just means all y. Under what conditions would it be true that the gradient of f0 of x transpose y minus x, when would that be bigger than 0 for all y? Well, I don't know. Let's figure it out.
Make the gradient identically 0?
That would work if the gradient were identically 0. In fact, that's the condition. That's if and only if the gradient is 0. Why is that? Well, if the gradient weren't 0, actually suggest a y. That ends the story right away. How about this y? How about y equals minus t times the gradient f of x at x, right there. There you go. Okay, so if I plug that in, then the first term here is minus t times the norm square of the gradient. Now t is a parameter. I can take it as big as I like, right? And I can certainly arrange it to be big enough to make this inequality true, right? Therefore, the only option is that the gradient itself vanishes, and we have reconstructed the high school condition, right? The gradient vanishes. Well, it's a little bit different from high school. Here's why. Because here it's a necessary and sufficient condition, right? So there it's a necessary condition. It's sufficient because of convexity. Okay, so we've reconstructed gradient equals 0 in this case the necessary and sufficient condition for optimality. Okay, how about an equality constraint problem? Well, here you'd want to minimize f0 subject to ax equals b. And here you can work out the conditions. It's not very hard, but it says that x is optimal if and only if there's a point in the domain with ax equals b and the gradient of f0, right, plus a transpose nu equals 0. Now you should recognize this as something like this is Lagrange multipliers. We will talk about this in complete detail when we talk about duality, but it's a hint. And this comes just from the same argument. That basically the argument would go something like this. You must have the gradient of f0 of x, transpose y minus x. That has to be positive for all y that satisfy ax equals b. Okay? Well, but wait a minute, because x also satisfies ax equals b. Right? So that says if I take the difference is the difference between x and y is in the null space, right? So we can rewrite it this way. We can say the condition is grad f0 of x transpose times z is positive for all z in the null space of A. All right, because if y satisfies ax equals b, it's a general element that satisfies that, right? And x satisfies ax equals b, and we do that because that's our second assumption here. Then the difference is in the null space of A, and vice versa, I should add. Okay? This says that the gradient has to make a non-negative with every element in the null space. But the null space is a vector space. So this couldn't, if this were positive, right? If this were positive for some z, minus z is also in the null space. And if I plug in minus z, I get something negative. So the conclusion here is that, in fact, you have to have grad f0 of x has to be, it has to have a zero inner product for all elements in the null space of A. Okay? That we can write. That says grad f of 0 of x is in the null space of A perp. I'm just rewriting. That's a macro. That's the definition. If you make a zero inner product with everything in a certain set, you're in the perp of that set, the orthogonal complement. That's this. And this thing, you'll remember from linear algebra, is the range of A transpose. Hey, that says that I can write grad f0 of x as A transpose times something. And the something I'm going to choose, I can write anything I like, but I'm going to write it as, how about negative nu there, okay? And I'm done. All right, so just using linear algebra and the general optimality condition, we recovered high school, what is it, maybe not high school, okay, Lagrange multipliers. Oh, except for one very important difference. This is necessary and sufficient here. Okay, here's one a little bit more involved. I won't go through the derivation, but it's minimization over non-negative ortho. So you want to minimize f0 of x subject to x bigger than or equal to 0. And if you work out the conditions, it's quite simple. It's this. X has to be bigger than or equal to 0, but that's feasibility. And the following. It says whenever xi is 0, the gradient here, the partial derivative of f0 with respect to xi has to be bigger than or equal to 0, right? And so you can actually figure out what that means. If this number were plus 1, it says that if you propose to increase xi a little bit, if you move it a little bit away, it says that the function goes up, right? What you can't have is you couldn't have this thing negative, because that would say then if you move a little bit in that direction, the function value would go down and you just got a better point. Okay, so I think this is, I mean, it's intuitive, but you can work it out directly from the conditions here. Well, the condition is very simple. Grad f0 of x transpose y minus x has to be bigger than or equal to 0 for all feasible y. Okay. So we've already said a little bit about equivalent convex problems, and I'll say actually just a little bit more. And we'll actually catalog some interesting typical equivalent pairs of problems, right? So we'll use an informal notion of equivalence. It's not the formal equivalence of reduction of one problem to another that you see in computer science, but it could be made formal, but there's no reason for us to do that. So the idea is two problems are equivalent if you can get the solution, if from the solution of one, you can get the solution of the other with modest work, and vice versa. In other words, what you could do if you want to think in a very practical way, you could think of this. If someone handed you a solver for one, you could write a wrapper that would be a solver for the other. And you have to have wrapper go both directions. Okay, so in other words, if you say this problem is equivalent to that, you have to be able to provide the wrapper that says, give me an instance of this problem, and then give me the solution of an instance of this problem, I'll get a solution of this problem, and vice versa. Okay, so let's look at some examples. By the way, we're going to use all of these things. So they're actually, we're going to use them later. It's quite important. So the first observation is this: eliminating equality constraints. So the way you do that is this. You have ax equals b, but we know what all x that satisfy ax equals b looks like. It's that's nothing but an affine set. And we can go to a free parameter representation. So free parameter representation says we first find a point that satisfies ax equals b. Oh, let me ask a question. Suppose on that step fails. So I attempt to find a solution of ax equals b and there is none. What do I do? If ax equals b has no solution, I can actually return, I can say, I didn't even look at f0 or fi, but I can tell you for sure your problem's not feasible because no point satisfies your equality constraints. Okay? Otherwise, you find one, and then you compute a matrix F whose columns span the null space of A. And then the general solution of Ax equals B looks like this. It's x equals fz plus x0. Now, normally the columns of F would be chosen to be independent, but that's actually totally irrelevant, in which case they're a basis for the null space of A. Doesn't matter, right? So what it is you compute matrices, a matrix F and a vector x0. X0 is, by the way, called a particular solution. And I don't know what the name is for F, but a basis for the null space or something. I don't know. Anyway, so that says that a general vector x that satisfies x equals b, that happens if and only if there exists a z, so that x is fz plus x0. Okay? I back substitute that, and my new problem looks like this here. And here we make a couple of comments. First of all, the following is true. This function is convex in Z because it's precomposition of a convex function with an affine function. These functions are convex in Z for the same reason. So the objective and the inequality constraints in this transform problem are convex. Okay. Now, then how would it work? How would you solve this problem if you had a solver for that? Well, I mean, it's extremely easy. You take an instance of this problem, you compute f and x0, you solve this problem here, and then that gives you z, and then you reconstruct x using this formula, right? So that's how you transform it. It's very simple, right? Oh, and you can go and vice versa. So that's how that works. But I do want to emphasize this problem and this problem are equivalent. They are absolutely not the same, right? And so if we call this prob and prob2, then for example, if I say prob dot equality constraints, right? And let's suppose that lists the equality constraints, what comes back is ax equals b. What happens if I take prob2 dot equality? Empty. Yeah, an empty list comes back because there are no equality constraints. So that tells you for sure those two problems are not the same. They're equivalent, but they're not the same. Okay. Now, by the way, a lot of people think it's a very naive view. By the end of the course, you'll know why. It's a very naive view that you should always eliminate equality constraints. The naive view is that you should always do that because, look, this is simpler, this thing, right? In fact, it has fewer variables, right? Because if x had dimension 100 and b has dimension 30, I'll assume everything's full rank here, z has dimension 70, right? So of course you would rather solve this because that's a problem with fewer variables. It's got 70 variables as opposed to 100 variables. That's number one. Okay. And number two, this one doesn't have any equality constraints. So it's sort of structurally it's simpler too. So you wouldn't imagine there'd be any compelling reason why you would prefer to solve this one. But we'll see later in the course there's a very compelling reason. And in fact, it's the opposite. In general, you would almost always prefer to solve this because you could always do this, but you'd do that if it were computationally advantageous. We'll talk about that later. So, okay. However, that relates to this, the next thing. You can actually introduce equality constraints, but some people refer to this, by the way, as unelimination. So to eliminate variables means to take an equality constraint, get rid of it, and so on. To introduce equality constraints, you're actually doing unelimination. It's the opposite. So here's an example. You want to minimize f0 of an affine function subject to fi of an affine function less than or equal to 0. So I just introduce a whole bunch of new variables, right? Which are the y0, y1 up to ym. And I rewrite the problem this way here. And here's the new problem, right? And so again, in the naive view, this does not look like progress. right? In fact, if you saw this problem, you might immediately eliminate the y's and end up with this thing, right? It doesn't look like progress because here's a problem that had no equality constraints, and you have created from it an equivalent problem that not only has equality constraints, it has more variables, right? Because the variables here are x and y0 up to ym, right? So it doesn't look like progress, but you'll see later things like this actually, very good things can happen sometimes in some contexts when you do this. Okay. Here's another one. Is introducing slack variables for linear inequalities. So here I want to minimize, say, f0 of x subject to linear inequalities here. And a very common trick here is the following, is I replace these linear inequalities with linear equalities. And I say AI transpose x plus SI equals BI, right? So that's and of course, and then I simply require SI to be positive. Now, this is silly because if you look at this thing, SI is, of course, BI minus AI transpose x. So saying AI transpose x is less than BI is saying SI is bigger than or equal to 0. So that's it. So what you would say is something like this. It says that if you can handle linear equality constraints and non-negativity, you can handle general linear inequality constraints. And this has several implications. One implication has to do with solvers. It says that instead of writing a general purpose solver, you can really focus on something that things are easily transformed to. Okay. Another variation has to do with the epigraph form, and this one looks almost laughable, but we'll take a look at it. Instead of minimizing f0 of x subject to fi of x less than 0 and x equals b, what we'll do is we'll introduce a single new variable called an epigraph variable. It's a new variable t. And we'll simply, we'll add a constraint that says t is bigger than f0 of x. Okay? Now, I mean, this is really dumb, right? Because look, this constraint, which by the way is convex. It's convex in xt, which are the variables, because f0 of x is convex, minus t is a convex function. It's linear. So this function here is convex. Okay? So you look at this, it's kind of dumb. This constraint here says nothing more than t is bigger than f0 of x. T appears nowhere else in the optimization problem. Therefore, if you fix x and you say what's the best value of t, the answer is, well, it's t should equal f0 of x. Why? Because that's the minimum, that's the smallest value t is allowed to go, but the objective is to minimize t. You could turn this around and say something like this. If someone solved, you would say something like this. If you solve this problem over x and t, then at the solution, t is equal to f0 of x, period. Right? If it weren't, then basically the person who alleged to solve it is a liar. Right? So that's the idea. Now, you might say, this is ridiculous. Like what? But actually, if you take a good look at this, it's very interesting. What it says, and some people say it this way. This says that some people say this. They would say that objective is universal for convex optimization. That's what they'd say. Because this objective is linear. I mean, t is a linear function of x comma t. So what that says is that if you build a solver for a linear objective, and you can handle, of course, you have to be able to handle the epigraph, right? But if you can handle the epigraph, then all you have to worry about is again making a solver that does that handles linear objective, and that's going to simplify a whole bunch of things if you have linear objective. We'll see later, but that's it. So that's why people would say a linear objective is universal for convex optimization. Oh, I should say something about these transformations. People who do this kind of stuff mostly know all of these transformations. And they don't tell them. They're not written down anywhere. Well, they're written down on these slides and in the book and everything. But basically, you're just supposed to know them, right? So and if you don't know these, so someone would say, oh, I need a solver for this. Someone would give you something else. It would actually solve an equivalent version of your problem, right? And you'd say, no, my objective is something more complicated, and you're just supposed to know this. Actually, we will see that a lot of these transformations can be automated, and that's what CVX does for you. Okay. All right. Next simple equivalence is what's called partial minimization. So partial minimization says You have a problem where you're minimizing f0 of two variables, right? x1 and x2. These are block variables. So I've simply taken x and I blocked them into two pieces, x1 and x2, and subject to, say, a bunch of inequalities only on the first one. I mean, and we could have equality constraints and things, but that's fine. Okay. Then what it says is we can, roughly speaking, we can minimize f0 over x2, which yields a function of x1. So I take f tilde of f0 tilde of x1, right, is this. It's the minimum over x2 of this function. Now that's convex because convexity is preserved under partial minimization. Okay? And then we have a problem that looks like this. By the way, if you take a problem with a big sequence of these, and instead of two, you have n of them, and you eliminate them one at a time, this is dynamic programming. So you've probably seen this. That's all dynamic programming is. It's absolutely nothing more than that. You want to minimize over a bunch of variables, minimize over one, and then the second one and the third and so on. So it's just something like that. These right now are all very abstract, these equivalences. So they probably mean nothing right now, but we'll see later, either in the context of applications or in some other setting where there's a target that we would say that we could reduce this thing by a transformation to this specific named problem. Then we'll see this will make more sense. So quasi-convex optimization. Here, you're minimizing a quasi-convex function subject to convex inequalities. Okay? Now, one thing you have to watch out for is you can have a locally optimal point that is not optimal in quasi-convex optimization. So in this case, that point there is absolutely, the idea is the derivative there is zero. It's absolutely flat. It is definitely locally optimal. Okay, here. However, it's clearly not optimal, right? Because if you minimize, you'd get something like that, right? So some things are true for quasi-convex optimization, other things not. In particular, local optimality does not imply global optimality for quasi-convex optimization. Okay, so how do you solve such problems? And the general technique is this. If a function is quasi-convex, what you do is you write it. What you do is you write a description of its sublevel sets in terms of convex functions, right? So the idea is you make a function phi sub t of x. It has to be convex in x for each t. And we arrange that the t sublevel set of f0 is the zero sublevel set of phi t. In other words, you have a representation that looks like this. So you represent the sublevel set of f0 by a convex inequality. That's the idea. That's what it. And by the way, you can show abstractly that for any quasi-convex function there is such a representation. Frankly, that's not very interesting because in any particular case there's something simpler. So here's an example. Let's take a ratio of a convex over a concave function where both are positive. P is bigger than or equal to 0 and q of x is positive on the domain of f0. That's a quasi-convex function. How do you check that? Well, what you want to do is figure out is the set of x such that f0 of x is less than t, is that thing convex? Now, if t is negative, it's convex because this set is what? It's the empty set, right? So this is the empty set, which is convex. If t is positive, then I'm going to substitute for f0 p over q. So this is just p of x over q of x is less than or equal to t. Q is positive, so therefore I can multiply through this linear inequality, and I can write that as p of x minus t q of x is less than 0. I'm done, because that is a convex function. P is convex, q is concave. T, with t positive, which is our assumption now, is non-negative, so tqx, t times q is going to be concave, minus, switches convex and concave, sum of convex is convex, this function is convex. Okay? So this would be the representation. This would be the phi t of x. Notice that it is not convex in x and t jointly, but for any fixed t, which is bigger than or equal to 0, this is a convex function. And the sublevel set gives you the sublevel set of F0. So that's the idea. Okay, so what do you do with that? Well, the idea is very simple. This says that we have a convex representation of a sublevel set. And what we'll do is we'll just vary T and check feasibility of the convex problem. So that's all you need to do. So here it is. If you want to do quasi-convex optimization, it works like this. We'll take what we'll do is this is the part that describes the sublevel set, the T sublevel set of the original objective F0. And so what we'll do is we'll guess a T. We'll solve this convex feasibility problem. If that feasibility problem is, well, if it's feasible, right? If the result is feasible, then we have found an X that satisfies all the constraints here and this. Because it satisfies this, that means F0 of X is less than or equal to T. If this is infeasible, then we know the following. We know that there is no X that satisfies all these constraints and has F0 of X less than T. And that tells us instantly that P star, the optimal value of the original problem, is bigger than T. I'm being informal. Okay, so if you want to do the careful analysis, you can look in the book or something like that, but I'm being informal here, right? It actually says it's bigger than or equal to P star. And if it's infeasible, it says P star is bigger than T. And so now you simply use a bisection method. So the bisection method goes like this. You start with an upper and lower bound on possible values of P star here. You start with these upper and lower bounds, and then you have an interval LU that contains P star, and you simply evaluate, you check for T in the middle of that interval, and it's either feasible or not, and either way your interval goes down by a factor of 2. Okay, and this tells you that it takes, exactly U minus L, that's your initial uncertainty in P star. It takes exactly that log 2 of that divided by epsilon iterations to converge to within epsilon of P star, right? And in fact, when you terminate, here's what you'll have. You'll have some very interesting things. You'll actually have a certificate. What you'll have is you'll have an X that will satisfy, it depends on the last iteration. If the last iteration was, let's say, feasible, you'll have an X where the sublevel set, where you'll have an X that's feasible and has F0 of X less than T. That's the final value of T. But you'll have a slightly smaller T, epsilon smaller, less than epsilon smaller T, where you've solved this convex infeasibility problem and found it to be infeasible. And so that constitutes a proof that F0 could not be less than your T minus epsilon. And so that's what you end up with. So that's how you solve a quasi-convex problem. Okay. What we're going to do now is we're going to talk about problem families with names, right? So we do this for a couple of reasons. One is historical. And in fact, it actually has less and less value as we move forward because things like CVX will automate a lot of the transformations for you. But for various reasons, you should know these problem classes. You can also know them because there'd be special solvers for each of these problem classes, right? So for many reasons, historical if none other, you need to know about these problem classes. Okay, and we'll start with linear program. I mean, which is actually, in some sense, it's the simplest possible general convex optimization problem. General in the sense of having constraints and other things. So it says all functions are affine, F0 and all Fi. And in that case, that says you minimize an affine function subject to linear inequality constraints. Well, affine, but we say linear, and linear equality constraints. So that's a linear program. Now, there's some silly things here. For example, this D is a constant, and so you don't really need it, right? You could remove it. A D does not affect the solution. And in fact, the way you'd write something without the D, you don't need the D, is you'd strip the D off, solve the problem, add D back in to P star when you return the solution to this problem. Okay. Now it's a convex problem. And the feasible set is a polyhedron because it's defined by linear equality constraints and linear inequalities. That's a polyhedron. And so this is a picture in R2. So it's a picture in R2, and here each of these is a row of gx less than or equal to h. That's what each of these is. This is a problem with at least 1, 2, 3, 4, 5, 6 constraints. And c points in this direction. Therefore, minus c points in that direction. And the semantics of optimization is please move as far as you can in this direction, right, while staying feasible. And so there's the optimal point. In this case, it turns out to be unique, right? So that's a linear program. So the picture here is simple. You obviously do not need anything to solve convex optimization, linear programming problems with two variables, right? So I mean, it's good to draw it this way, that's fine. But you should understand that, and you can pretend to visualize a polyhedron in R100. You should at least pretend to. I mean, and generally what it's going to look like, it's going to look like. The surfaces are going to be like hyperplanes in R100, and there'll be edges, and there'll be corners and points like vertices, right? Okay, but, we should all really understand that we're faking it when we do that, right? Because if you take a polyhedron with, 100 variables and 50 linear inequalities, something like that, you have something, the number of vertices, the number of edge, points like this is exponential and would be, for a problem of that size, extremely large, right? So it's still useful to pretend that we can visualize. So looks something like that. Okay, that's a linear program. Now, what's important about linear programming is, well, it's a convex problem. These can be solved unbelievably well, right? So this is basically a completely mature technology. This has been done like very well since like 1948. And so if you have a linear program with, a couple thousand variables and a bunch of constraints, it's just, that's something you can solve. I mean, depends on the number of constraints and the sparsity patterns and things, but you can solve that extremely fast and with total reliability on small things very quickly, okay? So that's why you would want to know about this. Right, so that's linear programming. Okay, so let's look at some examples, and the first one is historical. So it goes back, well, to 1948. And so we're doing it just because, it's historical. And here it is. So the original problem was something like this. It says you want to choose quantities, x1 through xn, of n foods. Okay, so these are the variables. And you're going to make a diet out of these, right? So it'll be 100 grams of this, 50 grams of that, 0 grams of that, something. And 1 unit of food, let's say a gram, costs CJ. And it has a nutrient amount, AIJ. Like, for example, nutrient 1 could be protein, right? So this tells you that a gram of this has, a third of a gram, 300 milligrams of protein. Doesn't matter, Nutrient 2 can be a vitamin. I mean, it doesn't matter. You get the idea. Okay, and so the idea is now you're going to construct a diet, which is a mixture of these foods. Now, by the way, you're not supposed to visualize this, like putting these things in a blender or something, because you'd come out with some brown goop or something. Anyway, so it's not supposed to be appetizing. That's yeah, I guess to make it appetizing, that's a non-convex constraint. But we'll talk about that later. Okay, so what you want to do is find the cheapest healthy diet. So in this case, you'd minimize C transpose X. That is, of course, the total cost. And subject to AX bigger than B, that says that you have here, AX is a vector that gives you a list of the nutrient amounts there. So, for example, entry 1 in AX would be the total protein. Say the next one is vitamin B. Entry 2 of AX would be the amount of vitamin B or something like that. Okay? And then B here is the minimum allowed level of that nutrient. Okay? Oh, and this is rather important. We're only allowed to do non-negative quantities. Right? So you can't do negative quantities. You can't go short, as you might in finance, on a diet. I mean, let's not go there, actually. Okay, we'll leave it there. Fine. Okay. Okay, so that's the problem. Oh, and here, this problem is still not quite in our standard form, right? But this is the kind of thing you get used to, people get used to, they don't do it. So let's go ahead and put this fully in our standard form. I'll do it once and then maybe never again. Here it is. You would rewrite it this way. Minimize C transpose X, and let's just go all the way, plus 0. So 0 is the D component. And now we have to write these as a set of linear inequalities, right? So we'll write it this way. Oh, and the linear inequalities, like all inequalities, our standard is that that's less than or equal to. So I'll rewrite this as minus AX here. I guess I'm allowed in this case to write it like that, right? I could go AX minus B is less than or equal to 0, like that. And then I can write minus X. Minus X is less than or equal to 0, right? And I'm still not done. I mean, this is kind of goofy, but let's just do the last step, and then we'll quit on this problem. So the last step is I would write that whole thing together as minus A and I times X plus, or however it doesn't really matter, minus B 0 there. There we go. Okay, so there we go. That's the official C. That's D. I forget what that is, maybe G, and maybe that's H or something. And we have it in our canonical form. So things like this, people don't even say that. They just say that's an LP, and then it's your problem to switch it around. Okay. Next problem is this one is only for historical. I mean, that's the only reason we mention it, right? Although, actually, it turns out an LP like this, I mean, something like a diet problem, it's actually, I mean, there's modern versions of it that are quite real, quite practical. I mean, so one example would be something like this. You would say that you have these would represent contracts. X is the amount of effort you put into some job or something like that. And then you might want to do something like minimize the cost of complying with a bunch of contracts, and it would be the same. By the way, you really can't solve these problems by hand if there's more than 20, 30 foods and 4 or 5 nutrients. I mean, you really cannot do it. I mean, well, you could do it, and in fact, I guess in the 50s, 60s, 70s, and even 80s, maybe even 90s, students were tortured with actually solving things like this by hand, and I'm not kidding. That probably goes on now at some places. Possibly even here. I'm not sure. But anyway, of course, that's completely silly. But the point is, it's not you can actually solve these by hand if it's tiny. But even if it's just small, you can't do it by hand. Anyway, it's silly. You shouldn't. Okay. Next one we're going to look at is piecewise linear minimization. Right. So here you want to minimize a function which is piecewise linear. It's the maximum of a bunch of affine functions. So it looks something like this. This objective function here. You have a bunch of functions like that. These are affine functions, and the minimum is that piecewise linear function, and you want to find a minimum of it. Okay. Now I want to first mention a couple of things. The first is that does not look like an LP, right? Because when you look at this problem, the objective, I mean, the whole point about an LP is that the objective is linear. This objective is highly nonlinear. So there we got a problem right there. So if you ask, is this an LP? The answer is it absolutely is not. Okay? It's not an LP. So that's the first thing you'd remember. Now I should mention something else. You've already seen this idea that there's a very easy way to create a piecewise linear approximation of a convex function. You evaluate, if it's differentiable, for example, you evaluate its gradient at a bunch of places. That gives you a lower bound. You take the maximum of it, that's still a lower bound, and it's a good approximation. Everybody got that? So this is actually a cheap and dirty way to solve a convex optimization problem. You have some F0, you don't have any other way to do it. You evaluate its gradient or draw some pictures, but in any case, you get a piecewise linear approximation of it, and then you will see that you transform this to an LP and solve it. Okay, so here it is as an LP. It's just it's nothing but the epigraph representation. You introduce a new variable. This is an LP, right? So that's what it is, because here you're minimizing a linear function. T is a linear function of xt, subject to these are linear inequalities. Now again, to get this exactly right, you'd put the t on the left-hand side and all that sort of stuff. We're not going to do that. Oh, And by the way, most people, they would actually call that an LP. Well, some people would. A lot of people would. If people who have to deal with piecewise linear minimization, they would say that's an LP. And that's slang, it's informal, and what it means is this problem is equivalent to an LP. And the practical implication is enormous. It says basically, since LP solvers are extremely reliable, extremely efficient, it says basically we can solve that problem. That's the practical implication of it. I mean, there are theoretical implications as well, but that's the practical one. Okay. So our next example of a linear program, or I should say a problem that can be transformed to a linear program, is the problem of the Chebyshev center of a polyhedron. So what is it? Well, I have a polyhedron, so that's defined by a set of linear inequalities. So here's the linear inequalities, and here's my polyhedron. And what you want, the Chebyshev center of this is defined to be the center of the largest ball that fits inside. Okay, so that's this point here, right? In this case, that's the Chebyshev center. So you really want to choose the center and maximize R, subject to the constraint that the ball fits inside. Now, actually, before we go on, I want to mention a couple things about this. The first thing is this. The problem clearly has applications immediately, right? Because basically what it's saying is, another way to say this, by the way, is to say find the point inside this set that is deepest inside it, has the largest distance to the outside. So in other words, if you were going to target for a manufacturing process, and these constraints define the acceptable region, and you wanted to have a margin so that if during the manufacturing process things varied, and you wanted the highest margin, you would choose the Chebyshev center. Okay? So this is already a problem that has applications. Now the second is, before we get into it, I want to point something out. When you think about a linear program, the whole point about a linear program is that all the functions that define it are affine. And so what should light up in your brain is things where the pictures you should see in your mind are flat things, hyperplanes, possibly with edges, right? Because we have inequalities and they would define edges. But you should picture objects that look like polyhedra and flat things. Piecewise linear functions, you remember that. That's our last example. Again, that's okay because at least they're flat. They're piecewise flat. Okay. Now, when I say ball, and that is a Euclidean ball, that is not. I can tell you a lot of things you can say about a ball and a two norm. But generally speaking, if somebody writes down a two norm, you're not talking flat, right? That's almost the canonical definition of curved. So if someone writes down a ball, if someone walks up to you on the street and says, I have a problem, and the first thing they say is, if they use the word Euclidean ball, it's probably, you would think, no, that doesn't sound right because linear programs pertain to things that are flat. So all I'm trying to do is set you up to say that this doesn't sound like this is going to end up as an example of a linear program. Obviously, it is. Otherwise, it wouldn't be in the lecture here. But my point is, it's not at all obvious why this would be the case or that it should be the case. And in fact, there's good reasons why you might imagine this wasn't going to happen. All right. With that preamble, let's take a look at the problem. What does it mean for every element of this ball here to satisfy a single linear inequality? And that says, here's A transpose X is less than B. And we want to know what are the conditions on XC and R under which this ball sits entirely in that half space. That's the question. Okay? Well, let's find out. Well, that's the same as saying we'll write the ball this way. It's the same as XC plus U, where norm U is less than R. That's the ball. It says that all of these numbers have to be less than BI. Okay, well, let's take a look at those numbers. Well, the first, it doesn't depend on U. So that just comes right out. So we want to find what is the largest possible value of AI transpose times U. Well, and we can vary U over everything that has length up to R. The Cauchy-Schwarz inequality tells you the following. It says that AI transpose U. This is less than or equal to the following. Norm AI, right? And then norm U, right? But that is less than R norm AI 2. That's the Cauchy-Schwarz inequality, okay? However, there's the converse to the Cauchy-Schwarz inequality. The converse says, when do you get equality here? And the answer is, oh, that's easy. It's when U is aligned with AI. In this case, that means U is AI over norm AI. And then we have to multiply this by R. There we go. So for this value of U, which indeed satisfies this, it is true that you get an equals here. And so that's that. That's the largest possible value of the inner product of AI and U over this set of U's. Okay, and we write this down. Again, it doesn't look like a linear inequality. It doesn't look like an inequality because we see this too. But we take a deep breath and stare at this for a while, and we realize that is, sure, that's a 2 norm, but its argument is a constant. This is a number. And if we look at this and we think of just xc and r as sort of the variables here, that's a linear inequality. So we have a linear program. It says we should maximize r subject to, that means find the largest radius, subject to this constraint. And if you were writing code, you would put a comment there. And then after the comment, you would write the following. You could say this is the condition under which AI transpose X is less than BI for all X in B XC R. So that's the ball with center XC and radius R, right? And that's it. It's that simple. So finding the Chebyshev center of a set of a polyhedron given by a set of linear inequalities, it's a linear program, right? But it has a lot of implications. It says you can do design centering and things like that using linear programming. I should say linear programming. We'll see that. That's part of a theme of the course. But things like linear programming can be done very effectively, even for relatively large problems. Okay. Here's a significant sort of generalization of linear programming is what's called linear fractional programming. It's a quasi-convex problem. And it's this. We have linear inequalities, linear equalities, and the objective is what's called a linear fractional function. It's a ratio of two affine functions, and there we do have to say the domain is one of the half spaces, and the convention is it's the half space under which the denominator is positive. Okay, so that's called some people call it a bi-affine function. No, they don't. No, some people might. By the way, in some small sections of mathematics, people would actually refer to that as an affine function. So if you did projective geometry, you would call that affine. Okay, but in any case, it's for us, it's linear fractional is one name for it. Okay, now that is a quasi-convex optimization problem. How do we know that? Well, all we have to do is look at what does it mean to say that f0 of x is less than t, right? There's the sublevel set here. And f0 is this ratio. The denominator is positive. So that's the set of x for which, and I should add that, the denominator is positive, right? Right? And I clear it, and I get C transpose x plus D plus T times E transpose x plus F is less than or equal to, in this case, let's see. I said this is less than or equal to T, and that's less than 1. Okay? So that gives me that. Sorry, did I get that right? No. There we go. Now it's right. Okay? So that's the condition, and I'll close the brace. Okay? So this is, for any fixed t, that expression, that inequality is a linear inequality, right? So that tells you that the sublevel set is an open half space intersected with a closed half space. And that is a convex set. Okay? In fact, you don't get points like this on the boundary, but okay, that's fine. All right. So you can solve this by bisection. Now it turns out that there's a very clever trick which allows you to solve this linear fractional program by solving a single LP instead of solving, let's say 10 LPs. If I solve 10 LPs by bisection, I can make my error in the objective go down by a factor of 1.024. That's 2 to the 10. But you can actually solve it exactly in one. I won't go into the details. The argument's a bit long, but you'd have to make the argument. And it basically is this. You solve the following LP. You minimize C transpose Y plus DZ, subject to GY less than HZ, AY equals BZ. So these are all completely legit. And in fact, these are all homogeneous. Well, no, sorry, that one's homogeneous. And the only thing that homogenizes it is this constraint E transpose Y plus FZ equals 1. So I won't go into, in the book, it's described in great detail how it is that solving this LP actually solves this linear fractional problem. Okay. Generalized linear fractional problem is the maximum of a bunch of linear fractional functions. It's the maximum bunch of quasi-convex functions, so it's quasi-convex. Fine. And therefore, you can solve it by bisection. And in fact, in this case, in general, there's no transformation that allows you to solve this with one linear program. Actually, that's, I guess, maybe not known or something like that, but I'm asserting it. I'll say it this way. I don't know of a way to write a generalized linear fractional problem as a single linear program. Okay. Very, very interesting example of this problem is the so-called von Neumann growth model. So in the von Neumann growth model, the way it works is this, is we have variables, x, and let's say x plus. These are variables, and they have to be bigger than or equal to 0. So that's a squiggly bigger than or equal to. They're non-negative. And what xi represents, that is the activity level of sector I in an economy. Then if you put the plus there, that's the activity level in sector I of the economy in the next period. For example, the next year, let's say. Okay, next quarter. It doesn't matter. Well, it does matter if you actually do this, but for us it doesn't matter. And so that's the idea. And a sector might be something like, transportation or defense or something like that, right? Okay. So here is von Neumann's model. It says if you look at xi plus over xi, that's a beautiful interpretation. That is the growth. Well, if it's bigger than 1, that's the growth in the ith sector of the economy. Because xi plus is the economic activity in the next period, and xi is in the current period, and the ratio, well, is the ratio. If that's 1.05, you would say that the economy grew, that sector of the economy grew by 5%. Okay? By the way, if that's 0.96, you would say that it shrunk, it contracted by 4%. Okay? And the von Neumann objective is this. You take all sectors of the economy and you look at the minimum across all sectors, right? So, and then that is something you want to maximize. And that sounds great, kind of egalitarian minded. So it's very nice. It says that basically, so for example, if this objective is 1.04, that's great. That means you had 4% growth in all sectors. That's what it means. If this is 0.92, that's not great because it says at least one sector shrunk by 8%, contracted. Okay? Now we have to talk about the constraints. Well, of course, there are the constraints that that x plus is bigger than or equal to 0. The xi's are, by the way, are positive already because the domain of this implies that, and so will the next constraint, but we'll get to that. Then it says there's a constraint that couples x and xi, and that's this. So A is a matrix that when you multiply it by x, its ith component gives you the amount of goods consumed due to activity sector x. right? So that could be, that doesn't matter what the goods are, but you know, it's a set of goods that could be natural resources. It doesn't matter what it is. Natural resources may be a bad example, actually. It's the amount of goods this is produced. Okay. Then B is a matrix that when you multiply it by an activity level, tells you the amount of goods consumed due to that level of activity, right? So that's the idea. So for example, you would take electricity, would be one of these entries, right? And then B, one of the rows in B, let's say the first row represents, let's say, energy produced. This would be, so the first row of B times X plus gives you the amount of energy which is produced. That's also, for example, because it assumes you have to store it or something like that. But okay, anyway. All right. And this constraint says the following. It says that the amount consumed in the next sector can be no more than the amount produced. Sorry, the amount consumed in the next period cannot exceed the amount that is produced in this period. That's what it means. And you could add it. You could add something else here. You could add a constant, which would be some stock of stuff you had of these resources you had beforehand. And so now the problem is to solve this. And that is indeed a generalized linear fractional program, because instead of maximizing, we could minimize, and then it would be the maximum, and you'd switch the ratios, and it'd be the maximum of a bunch of linear fractional functions. And you'd have a generalized linear fractional program. Okay. And the idea would be to determine the activity to maximize growth rate of the slowest growing sector. Okay, and we can actually, I mean, you can solve it by solving some LPs. In fact, by doing bisection on LPs. We'll move on to non-affine problems. And we're going to follow actually not really the modern flow, but we're going to actually follow here the historical flow of these problems. And so people had branched out. Big generalization. Yet you still have linear inequalities, linear equalities, but you have a quadratic objective, and it has to be convex. Okay, so convex quadratic. You do have something called indefinite quadratic programs. It's a totally different deal, not a convex problem. Okay, and those are also in general very hard to solve. Okay, so this is a convex quadratic program, or if you just say quadratic program, the default is that it's convex when you talk to people about this. Okay, so that's a quadratic program. And the only difference is this. Here's your feasible set. It's a polyhedron here. And the objective function now, though, is quadratic. And the level sets are ellipsoids, right? So here are some level sets drawn. This is increasing values of the objective. And in fact, there would be a center. I don't know if it's going to be somewhere around there. And that's where this thing has its minimum value. Assuming P is positive definite, that would be at the point P inverse Q. Okay, minus P inverse Q. That would be the point that minimizes this unconstrained. And so the idea is to slip down these curves, go as low as you can while staying in the set. And in this case, that would be the optimal point. Okay, actually, very interesting observation. For a linear program, you can always find an optimal point on one of these vertices. And here, it's right smack in the middle of a face. But that's a quadratic program. And you can solve these very well. Okay, let's look at some examples. Well, here's the most basic convex optimization problem is least squares. So minimize norm ax minus b, 2 norms squared. It's also called regression. It's least squares. And it's got just an analytical solution, right? It's A inverse B, sorry, A dagger B, and that's A transpose A inverse A transpose B. That's assuming A is full rank. Okay, so that's if that's if A is full rank and skinny. Okay, but in general, it's given by the pseudo inverse, the Moore Penrose inverse. And what we can do now is we can add linear constraints. So that's very cool. So you add linear constraints to least squares, and what you get is this objective is quadratic. It looks like this. It's X transpose times A transpose A, that's positive semi-definite, right? Minus, and then this will be transpose X, and this is 2 A transpose B transpose, right? And then plus norm b squared, right? You're minimizing, so this doesn't really matter, okay? That's a convex quadratic objective. And I can add constraints. For example, I could bound x between numbers. I could say, I could have a regression problem, and I could say, please fit my data B with a linear combination of the columns of A. But I don't want any of the coefficients in that linear combination. They can never be more in absolute value than, they have to be between -1 and 1. There we go. I could say, find me the best fit here where the x's have to be bigger than or equal to 0, right? So that's basically, this says, find the closest point B to a subspace. If I constrain x to be bigger than or equal to 0, it says find me the closest point to B in a convex in a cone, right? Which is A times x, where x is bigger than or equal to 0. Oh, another fascinating example of this, we'll look at many of these later, but here's a really cool one. Let's do least squares. And some people, there's a name for this. It's called, like, I think isotonic regression, right? That's the constraint that these are ordered like that. All right, there's no analytical solution for the best x that increases, but which minimizes norm ax minus b squared. There's no analytical solution to that, but that's, you can solve this by a QP. It's a very simple QP, right? This says it's minimize this quadratic objective. That is a set of n minus 1 linear inequality constraints. Things like x1 minus x2 is less than or equal to 0. Okay, so you can do regression, and you can add arbitrary constraints to regression, and you get a QP. Arbitrary linear constraints, inequalities, equalities. Okay. Now, another interesting case is when you do mean variance trade-off. So let's look at that. Let's suppose that we have a linear program with random costs. So C transpose X is the objective here. But we're going to say that C is a random variable. In other words, it's a set of prices, let's say. You don't know the prices. I mean, presumably you know something about the prices, but they may not be what you think they are. And we're going to model those prices as a random vector. And we'll imagine that C has mean value, C bar, right? So that's the mean price. And then it has variance, so expected C minus C bar transpose is sigma, is covariance sigma, right? So C bar and sigma describe some of the statistics of the cost, right? Okay. Now, what we'll do is we'll minimize here C bar, that's the mean expected cost, and that's plus gamma times, that's the variance. That's what this does, okay? Gamma is a positive constant here. It's positive, and it's called the risk aversion parameter, because the larger you make gamma, it says the more you care, in this case, by charging yourself, you're minimizing, it irritates you that the variance of the cost is high. So that's what this is. So that's the idea. And you would solve this problem for various values of gamma and look at it to see where you would be comfortable, where your comfort is in trading off risk. This is generally associated with risk, and then this would be something like just cost. Okay. Okay. Now something in between, or the next step up, is you say, well, look, if the objective can be quadratic, why not the constraints? Okay, fine. That's called a QCQP. Again, this is the historical evolution. So these days, I guess out of historical respect, people still talk about QCQPs, but nevertheless, we'll see that there's something that subsumes this nowadays. That's a generalization even more of this. So QCQP is a quadratically constrained quadratic program, and all of these matrices have to be positive semi-definite because all of these functions are convex. Okay? So that's a QCQP. Notice that this includes QP as a special case because I just take all of these PIs to be 0. Okay? And by the way, it includes LP as a special case too because I take this P0 to be 0. So the three problem classes we've looked at so far, which is linear programming, QP, LP, QP, QCQP, they're growing, right? We have LP, this is very rough, but you know what I mean. That's a subset of QP, and that's a subset of QCQP, right? So that's the picture so far. Okay, we're going to look at something even bigger. It's called second order cone programming, or SOCP. This is modern. This is the modern one. Okay, now second order cone program looks like this. It says minimize a linear function. Well, it's kind of like a LP. Subject to equality constraints. Well, they have to be linear. It's convex. And then subject to the following. There's a 2 norm and an affine part. And you look at that, and it sure looks like, kind of a QCQP or something like that. I'll get to that in a minute. But so let's take a look at this. Basically, each of these constraints, this is called a second order cone constraint. And basically it says the following. It says AIX plus BI, comma, CI transpose X plus DI. That's in the second order cone. Okay? So it's the image under an affine mapping, right? It maps X into this pair. And so, it's an affine mapping. And then it says that has to be in the second order cone. Or another way to say it is it's the inverse image under an affine mapping of the second order cone. So that's what a second order constraint is. Now, oh, by the way, notice that if I took, for example, I can either take the dimension to be low, or I could take AI to make the dimension Ni 1. I could take AI to be 0 or something, and this will recover an LP. And in fact, I can express any QCQP this way, and any LP this way, because I just don't need these terms and I have an LP, right? So that's it. And this is more general than QCQP and LP. Now I want to mention something here, which is interesting. Now for us, we say that's a convex problem. And why do we know that? Well, we look over here at the constraints. The objective is linear, so that's not a problem. And we look at the constraints here, and we say, well, this is convex, and then the right-hand side is affine. So I could just as well subtract it and say norm AIX plus BI minus CI transpose X minus DI less than or equal to 0. But that function is convex because it's a norm. Norm of affine is convex, and affine is convex. So that's convex. Now, if you were in the pre-modern era of optimization, here's what would happen. People have encountered 2 norms for hundreds of years. Gauss did. Gauss wrote a book about 2 norm minimization, right? That led to least squares. And that's your hint. In the classical view, when you see a 2 norm, there's something that you want to do very badly to it. You want to square it. And the reason is this. A 2 norm is not differentiable when the argument is 0. After all, a 2 norm, it's in 1 dimension. It's an absolute value, right? So this doesn't look good. And if your whole worldview centers around differentiability and things like that, then this is bad. It's not good. Okay. But if you square this, the square of a norm expression, like AIX plus BI, 2 norm squared, that is that's a convex quadratic function. That is fantastic. It's convex, number 1. And number 2, this is even better, it's smooth. There's no point anymore. If you square the absolute value, you get the square, right? It's nice and smooth. Okay? You can take gradients, derivatives, whatever you like. Okay. So you look at this thing and you say, well, you know what I'm going to do? I'm going to square it because it's irritating me or something. So you'll square it, and you'll get this, CI transpose X plus DI. Now this is not, oops, I got to square that. Okay? Now this is not the same as that, because we have to add the constraint CI transpose X plus DI is bigger than or equal to 0. These two together are exactly the same as that constraint there. Okay? And it's looking really good, because I would subtract this and write that less than or equal to 0. And I'm in a great position here, because now I have that's quadratic, less than or equal to 0, linear inequalities, I got a QP. QCQP, I should say. Okay? So this is what you would want to do. Now, can you do this? It all looks good, and there's only one minor problem with that, and that is this. The quadratic part of this matrix is exactly this one. It's AI transpose AI minus CI transpose. Sorry, that's right. Okay, so that's what it is. All right, now that's positive semi-definite, so is that, but the difference is not necessarily. Oh, by the way, if the difference is positive semi-definite, great. You have reduced your general SOCP to a QCQP. But if this is not positive semi-definite, you have a QCQP, but it's one with indefinite matrices, right? So, and that sort of makes it hard. Now, of course, it's easy, but you don't know that. So, all right. So let me summarize this. I should say that in the older, more historical, conventional view, a two norm, without a square on top, irritates you because it's not differentiable, and you'd have an urge to square it. If you square it, you would get a problem that is quadratic. That's great, it's smooth, but it's not convex. So, okay. All right, so this is SOCP. So let's look at an example of SOCP. Oh, and I should say that if you were tracing the history, quadratic programming, we were at about 1952, 53. QCQP, not long thereafter. We are now, well, it depends. I mean, we're in the 90s, let's say, late 80s. It would be the very beginnings. You're in the 90s, maybe, something like that. So you're in the modern era when you talk about SOCP. So let's look at an example. Let's take a linear programming problem. Here it is. Minimize this. And let's suppose that there's uncertainty in C, AI, and B. That's the problem data. Now, of course, in any real application, there will be uncertainty in these. That's not true. There are some examples where there would not be. For example, suppose that you are trying to verify some mathematical conjecture, right? And then in fact, the data are exact. But other than except for that one case, right, in any practical application, all of these things derived from, well, your problem. They derive from your problem, right? So, and there, I'll have a little side discussion about problem data. Zeros in the coefficients, they are probably really zero. They might not be, right? That could just be your way of saying small. Think numbers like 1/2, -1, +1, those maybe are exactly ones, -1s. Every other number, if you see a 0.236 or a 1.682 or something, all of those numbers have a provenance. They trace back to something, right? They trace back to some combination. If it's a physical thing, it's Young's modulus times a distance, right? It's some coefficient of thermal expansion. If this is finance, it will trace back to some parameter in a model, like the volatility or the mean return or something like that. So in all cases like that, those numbers are suspect, right? And it should be the case that if you vary them a little bit, the solution does not change wildly. Okay? So if it does change wildly, then it tells you that solving this problem is, as a practical matter, useless, right? Because I could hardly tell you, oh, I've got a wonderful way to land an airplane. It's absolutely unbelievable. Wait till you see it. And they say, how did you do that? Well, I solved a linear program, and someone said, that's great. And I'd say, there's only one minor problem with it. You need to know the mass of the airplane to 7 significant figures, right? So if there's any error in the 7th or 6th significant figure in the mass, then it won't work at all. Well, I mean, that's just stupid. It's not. That's just a non-solution. It has no practical use anyway. All right, so all that was just a long aside about variations in problem data. So, and there's a new trend now where people are explicit about the data, variations in data, and we're going to look at that now. So, For simplicity, let's just assume that the only thing that's going to change is A. So for some reason we know C. Actually, we already looked earlier at the problem of C being unknown, that we interpreted that as prices or something. So let's assume it's only A that changes. You can interpret A, by the way, as something that tells you how much resources you consume. Okay. Now the deterministic model says something like this. It says that I have some sets, EI, let's say an ellipse or something like that, and it says that each AI is in that ellipse. And I'm going to insist that that constraint hold for every single possible AI. So that's my constraint. And some people call that a worst case model. Well, because that's what it says. It says I want my resource consumption to not exceed the resources I have. My consumption should not exceed my resources, even in the absolute worst case. So that's that. Now another model is the stochastic model, and that says that these AIs are random variables, and the constraints have to hold with some probability. For example, I don't know, 90%, 99. Typical ones would be, in fact, things like, these are the ones of interest, right? There's not that many of interest, frankly, right? And there's maybe one more, something like that, right? These are the three of interest. Now, you might ask, why do I say these are the only three numbers of interest? And it's very simple. You don't care about like 0.7, right? That says, yes, I'd like those constraints to hold 70% of the time. That doesn't make any sense, right? Because, well, it doesn't. You want it to fail? You want it to be violated 30% of the time? I don't think so. Okay. 9.5, it's just kind of your way of saying I want it to usually be satisfied often. I want it to be rare that it's violated. Like once in 20 times. Okay. This says, no, I want it actually rarer than that, like 1 in 100 times. And this is basically your way of saying, I want it to be quite rare. I'll accept a violation, but it should be like 1 in 1,000 times. But already this doesn't mean a whole lot because when you put numbers like that on here, it sort of has a different meaning because this says you better be very certain of the distribution of these things. And when these are used in practice, in order to assert that a probability is 0.001, if it's 0.1%, you better be really sure of the tails of your distribution. And I can tell you that in practice, the one thing people do not know about distributions is the tail, right? Period. So, I mean, there's no way somebody can say, oh, yeah, yeah. So that's why you don't talk about something like this. Now, they do, okay? But when they talk about that, you have to understand they don't really mean the probability that you violate is less than 0.01%. They don't believe that. I mean, let's hope they don't believe that. What they really mean is this is a surrogate for saying, I really want that to hold, like very, very often. That's what they mean to say. Okay. I mean, they don't really care about the exact value of that number. Okay. So that's the stochastic model. Okay, let's look at the deterministic approach. Let's see how that works. Let's say that the ellipsoids, these are ellipsoids that describe possible values of the AI. Oh, and you might ask, how do you get these? Well, these are problems we'll even look at in this course. How do you get this ellipsoid? Well, the answer is you'd look at A1, right? That's a vector that characterizes the resource consumption of, for the first resource. And what you do is you'd go get a model of this thing from Monday, Tuesday, Wednesday, Thursday, and you'd get different AIs, and you'd get a year's worth. You have 365 different vectors AI. And if they're all over the place, then it's time to give up and go home. But if they're kind of reasonably tightly concentrated, you might fit an ellipsoid over that. We'll see exactly how to do that later in the course. You'll fit an ellipsoid over it, and that would be your ellipsoid. I'm just saying, where do you get the ellipsoid? Okay. So you have an ellipsoid. It's characterized by a center, and the matrix pi, which is positive, well, here we haven't yet assumed it's positive semi-definite, well, it actually doesn't even have to be non-singular. That it's an ellipsoid. This is a generalized ellipsoid. If p has less than full rank, it means that there are some dimensions in which AI is known exactly. Okay. The robust LP says this constraint has to hold for all AI in an ellipsoid. But wait a minute, that's this. That says that AI bar plus PIU transpose X, that's the maximum value of this thing here, has to be less than B. That has to be less than BI, and that's got to hold for all U. But we can just multiply this out, right? That's AI bar transpose X plus, and then that's the norm of PI transpose X. And that's from the converse Cauchy-Schwarz inequality. So basically it says this constraint becomes that. We now sit back and take a look at what we have. Linear objective. That constraint is linear plus norm of affine, 2 norm of affine, less than constant. That's an SOCP, right? And that's it. And by the way, the meaning of this, this is something that not, only some people know about SOCPs now, but 25 years ago, 15 people knew about them, okay, or maybe 20. So it's an extraordinary thing because there's a very practical, the practical conclusion is we can solve this with extreme efficiency and reliability. And in fact, this is already happening, that most fields, many fields that use linear programs are switching to SOCPs just to handle the robust case. Okay, and let me say a little bit more about it. It's actually super cool. If I get rid of this, this says please make. If I get rid of this thing, it says simply make the inequality hold when I put in the center of the ellipsoid. But that's not right because A is going to vary, and I want some margin there, right? So if I want this says I have to. So this is to be interpreted as the margin. And what it is it's a beautiful thing that tells you that depending on X, it tells you how much margin to leave. And the answer is simply P transpose X norm 2, right? And as an example, let's go to this thing. Suppose X is 0, and I ask you, do you have to worry about variations in AI? And the answer is no. And I'd say, really? Even if AI changes hugely? And the answer is no, not at all, because AI transpose times 0 is 0. So if X is 0, you don't have to worry about variations in A, right? Whereas if X is big, you do, because, well, roughly they're getting multiplied they get multiplied together. And so this thing says that the margin has to scale with X, and it even scales with the shape. If X moves in a direction where the ellipsoid is very big, then you have to have more margin than if you moved in another direction. Okay, it says, summary is this. You can solve deterministic robust LP via SOCP. Okay. Let's look at the stochastic approach. Well, the stochastic approach is this. AI is Gaussian with a mean AI bar, and a covariance sigma I, right? So they're Gaussian. Then that's a Gaussian scalar random variable, right? And that says that the probability that the constraint holds is simply the cumulative distribution function of the normalized version of it. So that's the margin divided by, this is something that has, that's a variable that has, 0, 1, that's n0, 1 here. Oh, sorry, no, well, yeah, it is. That's an n0, 1 variable. And sorry, if I put an AI there, it's an n0, 1 variable. And then this simply gives you the probability, right? Okay, so the robust LP, which looks like this, becomes the following. Oh, and we have to be very careful. It's this. To say that this is bigger than that, you need this probability here to be bigger than that. This is this thing here is an increasing function, of course, with X, and it says that you have to have this here. Now, the problem is this: if this thing is negative, then this has the wrong sign, right? Otherwise, if this is positive, that's a second order cone constraint. If it's positive, and that's exactly for eta bigger than 1/2, right? So it's quite beautiful what this says. So the interpretation is this: if you say solve me the stochastic linear program with let's say Gaussian AI, and with confidence level eta. And that means I want the constraints to hold with probability eta. We already discussed what etas you're interested in. You're interested in 0.9, 0.95, 0.999, something like that. These are the ones you're interested in. Okay, for those, you get an SOCP. You solve it. But what's super interesting about this is the following. Mathematically, it says that you get a convex problem provided eta is bigger than 1/2, right? So you get a very strange thing. Let's write down some values of eta here. Let's have 0.1 and 0.9, right? So there's asymmetric interest in whether we can solve this problem. That's interesting because that's robust optimization. That says I want the constraints to kind of hold 90% of the time they can violate 10. I don't want this. I mean, unless I'm absolutely desperate. This says, please find an x for which each constraint holds 1 in 10 times. So you don't do that. I mean, well, it all comes down to risk aversion, right? If you are averse to risk, this is quite bad, right? If your success rate is 10%. Now, by the way, if this is some act of huge desperation, you might take 10%. But generally, we're not interested in it. And that's super good because guess what? You can't solve that problem anyway. You can solve this one because it's an SOCP. These are actually quite difficult problems and you can't solve them anyway. So you get this weird asymmetry. Here's two problems. As a practical matter, these are the ones we really want to solve and we don't really care about these. And then, as fate would have it, it turns out the computational complexity of the two problems is hugely different. And it turns out the one we want to solve is exactly the one we can solve. The one that we don't really want to solve is the one we can't solve anyway. So, I don't know, it's kind of cool. I mean, you might imagine a world where we would have two versions of various problems and there'd be the ones we want to solve, the ones we don't want to solve, the ones we can solve, the ones we cannot solve. And you might imagine they might split as 0.25, 0.25, 0.25, 0.25, right? So, in other words, whether or not we can solve a problem is independent of whether we want to solve it. But, and this is just as a weird, I mean, don't take any of this too seriously, but as a weird observation, the following holds. There's strong correlation between the problems that we want to solve and the ones we can. So it's bizarre, but it's to be true, and this is an example of it. So the next application we're going to talk about is geometric programming. And this is fun because it's in a different group, a different type of convex optimization problem. It's one that in one form, in its natural form, is actually not a convex problem. So it's a problem, well, we'll see, it's not convex, but you change variables and it becomes convex. So that's what's interesting about the next class of problems. So that's geometric programming. So first, a couple of definitions. In geometric programming, you refer to a monomial as a function that looks like this. It is a product. They're variables. The variables are all positive in geometric programming, so they're all positive numbers. It's a product of these variables, each one raised to a real power. So these coefficients, a1, a2, up to an, they can be negative, they can be fractional, anything. And the coefficient has to be positive. And this is called a monomial. Now, I should say that there is a definition of monomial. It's been used for 100 or maybe probably more than 100 years in mathematics. And this is like it, but it's not at all the same thing. A monomial in mathematics is a single-term polynomial. But there, these coefficients, a1 through an, have to be integers, non-negative integers, and the coefficient in front, c, can have any sign. So unfortunately, if someone says monomial, you have to determine whether that's in the very narrow context of geometric programming or whether that is in the broader context of just mathematics. Anyway, so we'll call it a monomial. Now, a polynomial is, I mean, in addition to being very, very awkward nomenclature, and it's supposed to be, I think, a combination of polynomial and positive. So anyway, who knows why this term was coined? This was coined in the early 60s. And it's simply a sum of monomials. So it has a form that looks like that. And it's not quite the same as a positive polynomial. However, if you have a polynomial with non-negative coefficients, that is a polynomial. But polynomials is much broader because it has these coefficients can be negative, the exponents, and they can also be fractional, which is not true for a polynomial. Okay, and finally we get to a geometric program. That is an optimization problem. It looks like this, and at first it's going to be something a little bit strange about it. It's minimize a polynomial, because all the f's are going to be polynomial, subject to polynomial inequalities, and the right-hand side is 1. Well, it has to be 1, because a monomial and a polynomial, the value for any particular x is actually going to be positive. So the value is positive, so you could never say, for example, fi of x less than or equal to 0. I mean, if you did, the problem would be very easy to solve. It's infeasible. So it's less than or equal to 1. And then the equality constraints have the form of a monomial equal to 1, right? So this is very, very different from what you would see in a convex problem. In a convex problem, of course, all equality constraints have to be affine. And here's one where these are decidedly not affine. One other connection to things people talk about in areas like mechanics, people talk about a scaling law. That's another name, by the way, for something like this. It's a scaling law. It says that something like f scales as x1 to the 1, x2 to the minus 2.3 or something. And so that's a scaling law. So some people would even call a monomial a scaling law. Okay, so that's a geometric program. And it is obviously not a convex problem. I mean, for example, square root of x is a monomial, which is, of course, therefore a polynomial. So I can minimize the square root of x, but the square root of a variable x is a concave function. It's not convex. And of course, you could have things like this. x1, x2 equals 1. The product, that's obviously not convex. But this is a GP. Okay. Now, the interesting thing about GPs, which are not convex, is that they can be transformed to be convex problems by, actually you take two changes of variables, and they're both very interesting, and I'll say what they are. The first one is this. All our variables are positive. So, as actually happens, I mean, a lot of people have just figured out for other reasons, when you have a problem setting where all variables are positive, it's actually often a good idea to work with the logs of the variables. Fine. And in fact, that's correct. If someone is telling you about a scaling law, they'll plot something on a log-log plot. The fact that the second log, that would be the log on the horizontal axis, is used, it's a logarithmic scale, that says that you should really work with the log of the variable. So we'll take yi's to be the log of the variables. And that means they're unconstrained. They're not constrained to be positive. I should say that there is an implicit constraint that a monomial and polynomial, that the domain is positive, right? And it actually has to be strictly positive if any of these alphas are negative, of course. Okay. All right. Now, if you take a monomial and you take and you write each xi as e to the yi, and you take a product of e to the yi's, if I take something like e to the y1 to the a1, and I take this product times e to the yn to the an, and I put a c in front of it, that's the monomial expressed in the y variables. But you know what that is? That has the form, I'm going to write it this way, e to the, this is exactly e to the a transpose y plus b, where b is log of c, the constant. And that's, of course, where we need, this is where we need c to be positive, right? And so that says that a monomial in the variables y, in these logarithmic variables, is actually an exponential of an affine function. Okay. Now, if you take the log of a monomial, you get an affine function when expressed in terms of, when it's expressed in terms of the logs of the original variable. So you would say something like this. A monomial transforms to an affine function with two logarithmic transformations. The first one is you work not with the variables, but with the log of the variables. That's sort of before, because you transform the variables. You then also transform the monomial itself. The monomial itself transforms, you take the log of it, and that transforms this into, so you do a posterior and a prior logarithmic transformation, and you end up with something that's affine. A polynomial, that's something that looks like this. Well, it's the same thing. Each of the monomials looks like that. It's an exponential of an affine function. You sum them. That is, after all, what a polynomial is. And you take a log, and you see something super cool, that the log of a polynomial expressed in logarithmic variables is the log sum exp of an affine function. That's it. So actually, it's really cool. Monomials have been transformed by a dual logarithmic transformation into affine functions, and polynomials have been transformed into convex functions by dual logarithmic transformation. By dual, I mean that you take the log of the variables and work with those, and also you take the log of the function itself. So that GP converts to this problem. It's minimize log sum exp of affine, subject to log sum exp of affine less than 0, and affine. And sure enough, it is a convex problem, right? And so the meaning is this. The practical meaning is that if you see a GP, we can solve it. We can solve it globally. We can do we can do anything you want. We can do it. We have strong guarantees. We can find the global solution, all sorts of things like that. It's basically, and sometimes people say GP is convex. Technically, that's false. This is not a convex problem, and if I write down an instance of it, it's generally speaking not a convex problem, right? You can do things like minimize the square root of a variable. You can handle equality constraints that say that x1 times x2 equals 1. These are not convex constraints, and yet we can solve this by change of variables, transformation. There it is. By the way, when you actually solve it, the data is the same. So not much changes. So in other words, in the GP, so the data are the same. To describe a GP, what I have to do is for each monomial term in the objective and the constraint functions, and for each monomial in the equality constraints, I have to give you the coefficient and the exponents. But that's the same here, right? And they simply are the coefficients here. So it's absolutely no different. Okay. Now you know what a GP is. And what's interesting now is it turns out this is something that, it goes back to the 60s. A few people know about it. Actually, remarkably, it was not known widely that this was a convex optimization problem, actually even into the 80s. So there'd be people who would write articles saying something like they invented a new method for GP and they could solve a problem, well, with up to 50 variables in a mere minutes or something like that. So it was only, yes, it was indeed in Moscow that it was observed that this transformation makes this a part of convex optimization. So any method for convex optimization can be applied to GP. Now, currently, that tells you can solve GPs with tens of thousands or many more variables using just completely basic methods. I should also mention there's actually a wonderful, the original book on GP, which in fact popularized not only the term GP, but also this bad nomenclature, monomial and polynomial. The book is absolutely wonderful. It goes through, and it actually it describes a whole bunch of GPs, applications to power transformer design and all sorts of other stuff. And in fact, the book focuses on problems you can solve exactly, right? So they reduce it to this, and they have maybe 2 constraints, 3 constraints, and something like that. And they solve these things exactly. And the very last paragraph in the book, just truly wonderful. The very last chapter says that that solving GPs in cases when you can't do it by hand, and I mean literally by hand, calculus. You get out your old pen and paper and start writing derivatives down and things like that. It says that it's entirely possible that by programming computers correctly, a computer could automatically solve a GP. So, I mean, anyway, I thought that was kind of cool. And it turns out that's a book from 1961 or something like that. The answer is, you fast forward whatever it is, 30, 40 years, the answer is you bet, and that's exactly what's happened. So, okay. So what we're going to do now is actually just look at, we're just going to look at one example of a GP. It is a non-trivial one, and it's taken from a book from mechanical design, and it's design of a cantilever beam. So here it is. We're going to design a beam. It looks like this. It's going to have segments here. And each of these beams, they're going to be connected, and then I'm going to simply put a force at the tip of this beam. I should say what our variables are. Our variables are these beams. We can do the height, so you can see the height here. That's hi. What you can't see is the width, because the width would come out of the page here. So that's the width of it. And what is completely clear is sort of that the stronger this cantilever beam, if it's bigger, then it's, I mean, if you have deeper segments and wider segments, it's stronger, it's stiffer. And it's stiffer means that if I apply this force at the tip, it says that the beam will deflect less, right? So roughly speaking, what happens is I can put a lot of steel in my beam, and I can put a big force, and it will deflect only a little bit. Or I can make these things pretty wimpy and flat and very very lightweight. But the point then is it'll be quite flexible. You put a force, and it'll bend quite a bit, right? And you probably also have some basic intuition about it. For example, if you've thought about these things mechanically, or if you fiddle with things or build things with wood or anything else, you probably have some intuition telling you that height gives you more stiffness than width, right? You may know that. If you're trained in mechanical engineering, you for sure know that, or civil engineering, you know that. But even if you don't, you should have that intuition, right? That, well, think of it this way. If I take a 2x12, it's a whole lot stronger if I set it end up like this and push on this end than if I turn it flat like that and push on that end. It's a lot stronger. So anyway, so the variables are, we're going to optimize the cross-sectional area of each segment. So it's actually kind of an interesting beam, right? It can actually change shape. It can be deeper, and it can taper to something thinner. I mean, who knows what it is, right? And here's what we want. We're going to minimize the total weight of this thing. That's the total amount of steel. I mean, if it's made out of steel. And that weight is usually a surrogate in a design like this for cost, something like that. So we'll minimize total weight. We'll have upper and lower bounds on the width and height. So we'll have a maximum and a lower and a minimum for each one. And we can do upper and lower bound on the aspect ratio. So you can't make something that has an aspect, that looks like this, right, where it's super thin and too high, and you can't make something that looks like that. You probably wouldn't want to make something that looks like that, but you can't do it anyway. So we'll have upper and lower bounds on the aspect ratios. What we'll do is we'll have an upper bound on the stress in each segment. So in each segment here, when you load it, there's actually a stress here. And I'm not going to go into what that is, or I will tell you exactly how it's calculated. And I guess if your background is in ME, you would know these formulas. But we'll have an upper bound on the stress, because one of the very simple models of mechanical failure is that you have a maximum allowed stress. And if you exceed that, you start getting plastic flow or something like that. But it doesn't matter. For this problem, we have a maximum on stress. And we have an upper bound on vertical deflection at the end of the beam. That's here. And that's going to be something like a surrogate. That is a surrogate for how stiff the structure is. If it deflects a lot, that's bad. It's not stiff. And if it deflects a little bit, that's good. It's a stiff structure. Okay. And the variables are the widths and heights, just to remind you. Okay? So, all right. Now the objective looks like this. It's the sum of Wi hi all the way up to Hn Wn. That's the cross-sectional areas. And if all these things have the same length, so you could multiply this by L. And I guess to really get a weight, you'd then multiply by density of steel or whatever the material is. I mean, that's just a positive constant, so we're not going to show it. But look at this function. It's a sum. Well, it's actually W transpose H. That for sure is not convex in W and H. There's absolutely no doubt about it. I'll tell you what this thing is, though. It's quadratic. So that is a quadratic function of W and H. But it is definitely not, I shouldn't have used the word definitely, is definitely not convex, because the matrix is not positive semi-definite, right? This is it's a term that looks like that. There's sort of an I and a 0 and a 0, and this is your WH, right? Right? And so this indeed looks like that. This quadratic form is this. But of course, this thing has split eigenvalues, and it's neither convex nor concave, right? So the point here is just to show this is not a convex function. Now, what is interesting is this is a convex function if you work with the variables log Wi and log Hi. So if you work with the logs of the widths and the heights, this convex function. Okay. Now the aspect ratio and the inverse aspect ratio, these are monomials because this is really hi to the 1, wi to the minus 1. And if you like, you could put in all the other h's and w's, but to the 0th power. Okay, so that's a monomial. These are monomials, these things. Okay? So those are monomials. Therefore, by the way, they're also polynomials, right? So for example, if I tell you that the aspect ratio has to be limited to 3 to 1, no more than 3 to 1, I can write hi over wi is less than 3. That is the same as 1/3 hi over wi less than 1, and that's a monomial constraint. Now, the maximum stress on a segment is given this way. It's 6 times I is the segment number, and I'm missing some constants in here, right? Some, things like Young's modulus and various other things. These things I'm just missing. I'm not showing here, and that doesn't matter. I is the length, is the section number. It basically tells you how far out the beam you are, the cantilevered beam. And it's divided by wi over, it's this positive constant times wi over hi squared. That's a monomial, right? So if I want to limit the maximum stress, that is absolutely a monomial. That is a monomial function. Now the vertical deflection is, to calculate it, you actually have to calculate the vertical deflection and the slope at each of the segments. And these are done recursively, and it's by a set of equations that works this way, and they work backward from the tip. And it says something like this. It says Vi is equal to 12 times I minus 1 times this thing. And I certainly won't go into any of this or where this comes from. That's that. And then Yi is then given by this formula here. And you start with Vn plus 1 is Yn plus 1 is 0, right? And here E is Young's modulus. And what we're going to do, the way I'm going to argue that Vi and Yi are polynomial functions. And I'm going to use a very important property. And so these are obvious things, but let me just mention them. The product of two monomials is a monomial. That's the first thing. That should be clear. In fact, let's just go back, because it's a set of simple rules. If you take a product of two monomials, you get a monomial. You take the product of the coefficients in front, and you add the associated coefficient exponents. Okay? Polynomials are closed under sums. That's clear. Positive scaling. That's clear. That's also clear for a monomial. And also things like, for example, you can take the square of a polynomial. That's a polynomial. So you have all sorts of obvious rules about how you can add and things like that. For example, here's another one for monomials. Ready? The ratio of two monomials is a monomial. Well, that's kind of obvious because you just simply divide one of these by the other and you can work it out. Okay. So there's a bunch of rules that tell you about which things are closed under which operations. Okay. Now let's look at these equations. These things start as 0. I mean, in some sense, that's a null monomial. It's not really, because for a monomial, the coefficient is supposed to be positive. But in any case, let's look at the first one, which is Vn and Yn. So these just go away because they're all 0. And we look at that, and that's a monomial. On the next step, if you look at V sub n minus 1, Y sub n minus 1, what you get is you get something that looks like that. And you're using the fact that these are monomials here, that these are monomial. It's a monomial plus a monomial. That makes it a polynomial. So by induction, all the VI's and YI's are polynomials. Okay, so that's what it means. And that's very interesting because we're interested in Yn. That's the deflection at the end. Sorry, Y0. Okay, so we write it this way. We're going to write Y1, sorry. We're going to write it this way. We're going to minimize this. That's a polynomial. Subject to, this is the way to say Wi is less than W max. That's a maximum width. That's a minimum width. That's a maximum height. That's a minimum height in each segment. This would be the aspect ratio maximum and the aspect ratio minimum. And then here I would have, this is the stress limit. That's also very simple. So far everything's been simple. But here, this one, we use the fact that Y1 is a polynomial function of the w's and the h's, and it's given by that recursion, right? So, by the way, the same as an LP, people will write down an LP not in the standard form because it's kind of weird. They actually write down an LP in general as, we're in the convenient way. So people don't really write these things. You would just write that and you'd say that's a GP. No problem, because everyone in their head would know how to convert this to that. And if you have a modeling system like CVX, you just write things like this, and that's automatic to transform to that. And so you would just write stuff like that. And you just write things like that, the ratio. And they would say that's a monomial, and you can have monomial less than a constant and monomial bigger than a constant. So something. So you don't write it, you would rarely write it this way unless you were going to raw call a GP solver, where you had to produce the data in the canonical form. These days with things like CVX, there's no reason to do that. It's just a waste of your time. So the next topic is generalized inequality constraints. And let me explain a little bit about what it is before we start. What we're going to do is we're going to look at these constraints here, and we're going to generalize these functions to be vectors. Okay, so that means up till now they've been scalars, right? So if you evaluate f3 of x, that's a number. And the requirement is less than or equal to 0. So if f3 of x is, minus 0.01, that's fine. If f3 of x is plus 0.01, that's infinitely bad. What we're going to do now is we're actually going to allow these things to be vectors. And we're going to see, what does this mean? We'll figure it out. Now, there we do have inequalities. These are inequality with respect to a cone, and so we'll have an inequality with respect to a cone. And our requirement here to be a convex problem is you have equality constraints is the only have to be linear. And the inequalities, here you have to have Fi is convex, is Ki convex, right? So that means that Jensen's inequality holds, but with respect to the inequality induced by Ki, okay? And there's several forms for these. Usually they're quite simple, but one that's very common now is something called a conic form problem. Some people would even call this the modern canonical form for a convex optimization problem. It's this. You minimize a linear function subject to linear equality constraints, and an affine function is less than or equal to 0 with respect to a cone K. And the idea here is if you take K to be r plus to the m, this describes a completely general linear program. But the idea is now you swap in a different cone and you get a different problem family. We'll see some very interesting ones in a minute. A lot of these things have names. We will see some of them. And these are mostly things that have come up in the last 15 years, something like that. The most famous by far is a so-called semi-definite program, or SDP. So this is the following problem. It looks deceptively simple. It says this: minimize a linear function subject to linear equality constraints and an inequality that involves just matrices, a single one. That's it. So it just says take an affine function of matrices, that's x1 f1 plus x2 f2 plus xn fn plus g. That's a symmetric matrix, and you insist that that be negative semi-definite. There. Oh, by the way, a constraint of this form is called a linear matrix inequality. And the idea is if I were to make this, this inequality here an ordinary inequality and make everything a scalar, this would be a single linear inequality. But now I just simply capitalize the f's and g's. So the left-hand side is now a symmetric matrix. And I take the inequality on R and I make it inequality on symmetric matrices. And I get a so-called linear matrix inequality. So that's it. So minimize linear function subject to equality constraints and a single LMI. That's what these are called. That's a semi-definite program. Okay? And that's an example of a convex optimization problem with a vector inequality constraint. Okay? So now there's a couple things we should say because it's important to know. Now it turns out you look at this and you say, why just one inequality? And the answer is something like this. If you have multiple independent LMIs, I mean, they're not independent, just if you have multiple LMIs like this, linear matrix inequalities, you can always throw them together and make one big one. And that's done, it's a very simple thing. All you do is you put these together on the diagonal of a bigger matrix like that. And the off diagonals are just 0. And you're using, the stunning fact that if you have a block diagonal matrix, then it's positive semi-definite if and only if each of the blocks is positive semi-definite. So the point there is that most people realize that you can have multiple LMIs, and that's the same as having one. So people still just say it's an SDP. Okay. Now it turns out SDP generalizes most of the classes we've seen so far. Not GP, but other than that, it generalizes them. For example, LP you can write as an SDP. You can write SOCP as an SDP. Of course, that's one's a stronger statement than the other because you can represent an LP as an SDP. Sorry, as an SOCP, and an SOCP can represent it as an SDP, right? So you can say things like we have the LP and SOCP embeddings as SDPs, right? And this has, I mean, it doesn't really, it has some implications. If and when semi-definite program solvers are completely perfected, this will be beautiful because you'll just have one solver for everything. And if it's an LP, you'll form a certain type of SDP and solve it. But okay, so here is a linear program. Minimize C transpose X subject to X less than or equal to B. And here's a semi-definite program that's equivalent. What we do is we're going to use a following stunning fact. A diagonal matrix is positive semi-definite if and only if all of its entries on the diagonal are bigger than or equal to 0. So this is simple. It's kind of silly, So you would say, what's an LP? And you could say, well, it's an SDP, but with diagonal matrices. But I mean, who cares? Okay. SOCP is a little bit more interesting. So how do you do that? How do you write this SOCP as an SDP? And the answer is quite interesting. It goes like this. This constraint, that's a second order cone constraint, that is a nonlinear constraint on X. Well, of course it's nonlinear, and it's not affine, right? This is affine, but that, of course, is not affine. And so what we're going to do is we're going to write a nonlinear, non-affine function or constraint as a linear matrix inequality. That's quite interesting because you're going to get something, the advantage is you're going to get something that's linear. Or let's look at it. So you write it this way. Now, that's the identity. That's a scalar. That's a vector, and that's a scalar. And it asserts that, it says that, and this is going to be by the Schur complement, right? That's the Schur complement idea. And the Schur complement gives you, well, it tells you various things about when a block matrix is positive semi-definite. And so that'll work this way. This matrix is positive semi-definite when, and we can write it either way. There's two ways to do it, but one is to say something like this. You would say that it's when this matrix is positive semi-definite, but that's a multiple of the identity. So that simply requires Ci transpose X plus Di bigger than 0. And the Schur complement of this matrix with respect to that, which is the following. And there's lots of ways to say it. You can also start here, but you'd end up with something like this. Ci transpose X plus Di plus then AI X plus Bi transpose times the inverse of that matrix, but that's the identity. So I'm going to hold that. I'm going to do some very rough notation here, and I'll simply put it down here. So you have to have that, and there's a minus sign here. I'm sorry. There we go. There we go. So that's the Schur complement. The Schur complement is, well, lots of ways to say it, but it's something like this. It's this. There's lots of ways. It's this minus that times that inverse times that, right? And so you get something that looks like that, right? Now this thing is positive, so I can multiply through by this, and I get norm AIX plus BI squared here. It's on the other side, is less than or equal to this thing squared. And I take the square root and I invoke this. And I get exactly this. Okay? So that's the idea. So you would say that you can embed a second order cone program as an SDP. Okay, let's look at another problem. It's, again, quite interesting. Let's minimize the maximum eigenvalue of a symmetric matrix, which is an affine function of a variable x. So, for example, I could have a matrix and I have some entries in it that I'm allowed to choose. Some are fixed, some I can choose. That would have this form. And the question is, how do you choose those entries in such a way as to minimize the maximum eigenvalue of this matrix, right? And before we start in on that, I want to point out, now you know this is convex, right? Because that's one of the main things we looked at. We looked at the maximum eigenvalue being a convex function of a symmetric matrix, and A is an affine mapping, so by composition rule, that's a convex function. But I want to point out how complicated this is. So if you were to tell somebody, how do you calculate this objective? The answer would be, well, you form this matrix A, okay? Then you calculate its characteristic polynomial, which is by taking a determinant, and you get this giant thing with n factorial terms, and you'd collect all the terms, and you'd get like s to the n plus, trace A of x times s to the n minus 1, and you'd get these coefficients. Then you'd be asked to find all roots of that. There would be n real roots, and you'd find them. Now, you may know that there's no formula for these roots if n is 5 or bigger. So there's not even a formula for this, right? There's a quadratic formula. There's one for cubics, one for quartics. There isn't one for quintics, okay? And then finally, you'd take all these roots and you take the largest of them, and that would be the largest. That'd be the biggest eigenvalue, okay? So the point is, this is very complicated in some sense. Well, if you describe it the wrong way, it's very complicated. But it turns out this is nothing but an SDP. It says minimize a scalar t subject to A of x is less than or equal to ti. And that's it, right? And that's a matrix inequality. And the reason is this. The maximum eigenvalue of a matrix is less than t if and only if A is less than or equal to ti in a matrix sense. The argument, you could make lots of arguments. You can argue with the eigenvalues or however you like, but this is just correct. Oh, and I should say, this isn't quite in LMI form, right? Although people would accept this as an LMI because the left and right-hand sides are both affine. You would subtract it. You'd write A of x, say, minus ti. And that would be it. There would be full LMI form. But that's the same as this. So, and by the way, what's the upshot of all this? Semi-definite programs are now quite tractable. They're solved all the time. I mean, it's not like linear programming, so it's not like it's used everywhere and it's super duper reliable. It works like quite well. And so there's a sense in which you reduce something to an SDP and it's sort of solved. And so what that says is you can minimize the maximum eigenvalue of a matrix, of an affine dependent matrix. Okay. We can do matrix norm minimization. Again, the trick is through Schur complements, right? So the idea is you minimize the 2 norm of a matrix. That's a symmetric, maybe not even square matrix A. Well, this is the maximum eigenvalue of A transpose A, and then the square root. Okay? So, and here A is a matrix that's affine in the variable x. And that's equivalent to an SDP. Let's see how. You rewrite it as minimize T subject to this matrix here being positive semi-definite. And again, the trick is Schur complements. This matrix is positive semi-definite if and only if, we'll start here, Ti is bigger than or equal to 0. That requires T to be bigger than or equal to 0. And Ti minus A of x transpose times the inverse of this times that is positive semi-definite. And that's exactly these inequalities here, right? And this inequality is also really interesting. That says this is exactly the same as saying that lambda max of A transpose A is less than or equal to t squared. That's what this says. Well, that was what we did on the previous page. Also, it's clear. Okay? But this, so therefore, if I take the square root, I get this, and that the power goes away. And that's exactly this right there. So that's the, in fact, it's the epigraph So a fancy way to say this is that the matrix 2 norm, the matrix-induced norm, the maximum singular value, its epigraph has an LMI representation. That's how you would say this. That's a sophisticated way to say this, right? And it's really cool. So it says you can transform a problem involving a matrix norm to an SDP. I mean, that's cool. By the way, this is exactly how CVX works. So in CVX, you can write down the norm of a matrix. It understands that that's convex. If you minimize it, what happens is exactly the argument here is converted to one of these block 2x2 matrices. And if you wanted to, you could even go in and look at it. You could trap the call before a cone solver is called, but you would actually see this matrix there. Okay? Okay. All right. Our final generalization of optimization problem is a bit more complicated. It's vector optimization. So what we're going to do now, just to set the context, the last generalization we looked at was we said, what if these constraint functions were vectors? And so then we had a standard idea of what it means for a vector inequality to hold. We're going to do something a bit more complicated here, and you have to be super duper on your toes with respect to the semantics. We're going to minimize a vector function. And by the way, a lot of people just say, well, let's minimize a vector function, but the thing is, you have to say what that means. So we'll say what it means in a bit, but it's not completely obvious, and it turns out you can have several meanings. Okay. So a convex vector optimization problem looks like this. You minimize with respect to a cone an objective that is a vector, right? And we'll leave the inequalities as scalar, and the equality constraints are, of course, just linear, okay? But the real question is, what does this mean? And what you have to do then is you have to go back to the original semantics of an optimization problem. So an optimization problem, the semantics goes like this. You give me x, and somebody else gives me another x. Okay, x and x tilde. The first thing I do with each one is I evaluate fi of x, and I check, do I always get a number that's less than or equal to 0? If I don't, I instantly throw that x back at that person who gave it to me, and I say, not feasible. It's completely unacceptable. Okay? By the way, the same thing would happen if they gave me an x that was out of the domain. I would say, that's even worse. I'd say, your point is so bad, I can't even evaluate the third inequality constraint function. Okay? So, and then I would check to see that hi of x is equal to 0. By the way, that is a typo. That should be equal. So I would check then to see if hi of x are equal to 0 for each one. And if they are, that's fine. If not, then I throw it back. If both x and x tilde are feasible, so they pass these tests, then how do I compare? How do I say one is better than the other? And the answer is extremely simple in standard optimization. I evaluate the objective, right? If you like to think of an objective as having units of dollars, go ahead. It's a cost. Anyway, whichever one is less, has a smaller objective, is better. It's cheaper. It satisfies all the constraints, and it's cheaper, it's better. By the way, if they're different, if x and x tilde are different and have the same objective, I can't say which one is better. They simply, as far as this problem is concerned, they're the same. So that's the idea. Now the problem here is this. If that's a vector, I have to have a way of saying one is better than another. But as you know, if you have two vectors and a vector inequality, you can have the very awkward situation where they're incomparable. So that can and does happen, and that's actually the interesting part. Now, when it doesn't happen, it's easy to say. If for example, this is a 2 vector and you're minimizing with respect to r plus 2, that simply means that each of the entries should be smaller than the other, and if you come back and one person has one where the inequality, one is better than the other, then it's clearly better. But we'll see what the other idea is. Okay. So what we'll do is we'll look at the set of achievable objective values. Now that's a vector. That's the point. So for every feasible point, conceptually, we will simply record the objective you attain, and we'll call that O for the set of all objectives. And here it is. By the way, for a scalar optimization problem, this is a simple thing. It's a subset of the line. Here's the line. And O might look like this. I mean, it could look like that. I mean, it's actually going to be connected in this case, so it'll be an interval. Okay, it'll look like that. And you'll say, okay, like for a convex problem, you'd say that's what it is. And you know, if there is one, if this is achieved, I guess I've drawn it as achieved, then whichever x corresponds to that point, that's optimal. Okay, but here it's a set in R2, like for example, this one or this one. Okay, and then we say the following. X is optimal if this is the minimum value of that set. Now remember what the minimum value said. The minimum value says that this point is comparable to every other point in the set and is less than or equal to it in the cone sense. So these are two pictures with respect to R plus 2. And it would say that there's a point here which is comparable to every other point up here and less than or equal to it, which means, in fact, it means that all these points are up and to the right. Okay? So that means, that says it's optimal. And, you know, by the way, it's a very strong form of optimal. It says basically that you can minimize both this objective and this objective simultaneously, and you get that point. I mean, by the way, if that happens, that's wonderful. It usually doesn't. The more interesting case is that O might look like this, something like that. Now it's more interesting because we can say, we can ask, is there a point in this set O that is comparable to all other points in O and better than it? And the answer is there a point where in this set where every other point in the set is up and to the right of it? And the answer is no, there's not. But remember, we have a weaker sense. This is minimum, and this is minimality, right? So there's minimum and minimal. And so we'll say that if f0 of x is a minimal value of O of x, then we're going to give the name Pareto optimal. That goes back about 100 years. Okay, that's the idea. Now, Pareto optimal is subtle. It says the following. It says that there is no point in the set that is better. Okay, now on the line, any 2 points on a line are comparable, and so these two concepts of optimality merge into one. But in a vector optimization problem, that's actually not true. They're different. And so here, for example, in this case, this point is Pareto optimal. And the reason is there is these, if you look down and to the left, again, this is with respect to R plus squared. If you look left and down, those are all the values which are better than the one you have. Better here means, oh, by the way, another name for this, like in economics, is it says that better is dominates. So you'd say that, for example, this point dominates that one because its objective value, which is a vector, is less than or equal to that one. So all of these points on this curve here are Pareto optimal, and then from here on down, right? These are not, and certainly that's not. And one way to say it is something like this. If a point is not Pareto optimal, then there is a better point in the set. Okay? So another name for not Pareto optimal is dumb. It's a dumb choice because it says that I can find a feasible point, x, which beats yours unambiguously, right? That it's less than or equal to in the cone. Okay. Now, a very common case of this is just multi-criterion optimization. That's when you have you're comparing with respect to the cone, non-negative orthant, and you like to, one way to think of that is vector optimization. That's another name for it. The objective is a vector, and you think of each of these as a separate objective function, right? So, for example, these might be, you know, in a circuit design, this might be power and area or something like that. You might have two of them. You might have two or three, power, area, and delay for a circuit. And then these are all things you want to be small. And so that's kind of the idea. In finance, these would be things like cost or negative profit. And then the second one might be some kind of measure of risk or something like that. You want low risk and you want high profit, which is low negative profit. So that would be also naturally a multi-criterion problem with two. That's called bicriterion. Okay, so you think of these as different objectives. And the idea is you want them all to be small. And you'd say that a point is optimal if this holds, if whenever x is, if x is optimal, if whenever y is feasible, you have f0 of x is less than or equal to y. And what that means is, it means that you have simultaneously minimized all objectives. Now that, by the way, rarely happens, right? This is what happens very often. A point which is feasible is Pareto optimal if the following is true. If you have another feasible point that is less than or equal to this one, then in fact they're equal. And that's the idea. And so roughly speaking, if you have Pareto optimal points, it says that there's a trade-off between the objectives. That's what it says. So let's do a simple case, regularized least squares. That says I would like ax minus b norm, 2 norm squared to be small. That means I want good fit, but I also want the norm of x to be small too. Now, in this case, we can characterize exactly what O looks like. We don't have to do it, but it's here it is drawn. And so the idea is, look, there's an x that achieves that value. Now, that's not very interesting, right? Because it's basically, it achieves a terrible value of fit, right? And at the same time, it's quite large. So it hasn't done very well on anything, right? Now, so all our focus is going to end up being on this little part here, okay? And on that little part there, this boundary is Pareto optimal, right? And we can even say what the different ones are. For example, this point right here is very interesting. It achieves a value of the size of x of 0. And so what x does that correspond to? It can only correspond to x equals 0. And so this tells you at that point that 10 is the value of norm squared of b. Okay? I mean, the numbers don't matter, but that's what it is. All of these points in here are Pareto optimal. And you would say there's a trade-off of fit versus size of x. That's that trade-off. And another name for this Pareto optimal curve is the optimal trade-off curve of fit versus size, for example. So this is the idea. A very famous case of this is in finance, so risk-return trade-off and portfolio optimization. This is due to Markowitz, and this is the early 50s, right? Very early 50s, right? 52, 53, something like that, okay? So, and the idea here is we want to minimize two things. This is negative profit, right? Or negative return, mean return, and that is return variance. So here, x gives you an investment portfolio. So xi is the fraction of things you invest in asset I. Then p is a vector of, these are asset price changes. It's a return. And that's modeled as a random variable with mean p bar and covariance. So the mean return is p bar transpose x. That's this one. And this is the variance. And so what this says is I want small variance and I want large return. By the way, it's traditional to put in one of the assets is cash or T-bills or something, and that's supposed to be 0 variance, right? So that's traditional in this model. Okay, so here, if I solve this problem, we can work out the trade-off curve here, and we'll see how to do that shortly. But you get something like this. You'd plot it. Here you'd plot the square root of x transpose sigma x, which is the standard deviation. And so that's like the risk, and that is the return, right? And so it would say that, for example, here's something where by investing all of your money in in whatever is the most riskless option, that appears to be the fourth asset here, because that's at 0. Here's it's all in x4, and that gives you a return of 3% and almost 0, or maybe even exactly 0 risk, right? So that would be T-bills, not now, by the way, but maybe 15 years ago. And then as you move up here, you can see these are the optimal points. These correspond to these different points here, probably, right? These kinks over here. And you would say that this is the Pareto curve. By the way, it's traditional to draw it this way and not the usual way. And the reason it goes up like that is because here good is up, and here good is to the left, right? Because you want low risk, high return, okay? And so If you were to switch this around to make it a negative, that would be going kind of the way you'd expect. Okay, so this is a very classic example of two multi-criterion optimization with two criteria, and in fact, you call that a bi-criterion problem. Okay, now, scalarization. How do you find Pareto optimal points? And the answer is pretty easy. You choose a vector, lambda, which is positive in the dual cone, and you solve this ordinary scalar optimization problem. Now, what's cool is if this is a convex problem here, the original one was a convex vector optimization problem. When you scalarize, you get a convex scalar optimization problem, which we can solve. And the meaning is really simple. What it is if you take a value of lambda, you take lambda like this, that's the normal. And it says basically go as far as you can in the minus lambda direction while still being in O. And so what you're going to do is you're going to get the tangent there. And so lambda sets the slope. And then what you do is you find the point that is tangent to the set of achievable values. And here it is for one lambda, and here it is for another value, lambda 1 and lambda 2. And what is always true, convex or not, is that if you carry out this procedure, you get points that are Pareto optimal. That happens always. Of course, if it's not convex, you can't solve that problem, but if you could, you'd get something that was Pareto optimal. What is very interesting is that when the original problem is a convex vector optimization problem, you get almost all Pareto optimal points. And the reason is, roughly speaking, it's because O is convex. That's actually false. O is not necessarily convex, but it's lower. We care about the lower left part of it, or roughly speaking, and that actually always is convex. We'll get to that. Now, for multi-criterion problems, when you scalarize, you are simply minimizing a weighted sum of objectives. I mean, this is very old idea. It's so intuitive that people don't even say it. I mean, ever since you took any class on anything, people would say, what are we going to minimize? We'll minimize this thing plus a little bit of that. You add some regularization, and someone says, what's that coefficient there? And you say that's a weight that you mess with, right? So it's weighted minimization, right? So here, that's the interpretation of lambda, is it's the vector of weights that relate these objective functions. And there's nice economic interpretation. For example, you could think of these F1 up to FQ, these as being some kind of cost or consumption, but they could be in different units. I mean, one could be in kilowatt hours, and another one could be in dollars. It could be a direct cost. And now you have to add them up. And you can actually think of the lambdas as a set of prices. For example, in that case, well, if the first one were dollars, lambda 1 would be 1. If FQ is in kilowatt hours, lambda Q has a beautiful interpretation. It's a price. It's the price in dollars per kilowatt hour. And it's whatever needs to happen. If you want to include the physical units in the lambdas, you're welcome to too. But it's whatever has to happen so that you can add these up and put them on the same scale. Another interpretation is that these weights are more abstract. They just tell you how much you care, how irritated it makes you if lambda, if the different ones, so if you had lambda 1 is 1 and lambda q is 10, that says, someone says, what's that all about? And you say, well, that just means that I find a unit increase in FQ to be 10 times more irritating than a unit increase in F1. So they're just relative weights. Okay, now, when you apply to the regularized least squares problem, well, you just get this. I mean, and there's our friend. Well, I guess in statistics you call this ridge regression, because you're minimizing a traditional least squares objective, and you add plus gamma times the norm 2 squared of x. And that's a least squares problem, and for any gamma we can solve this. And this will trace out this curve like this. It won't get you exactly that point. And since we're insisting gamma is positive, it doesn't get you this point either. But as gamma goes to 0, you get closer and closer, and as gamma goes to infinity, you get closer and closer to this point here. So that's the idea here. Okay, so that's scalarization. And in finance, if you apply it there, what you end up you minimize that's negative return, mean return, plus gamma times x transpose sigma x, that's risk. And so people would normally write that this way, that you would maximize p bar transpose x, that's your mean return, minus gamma x transpose sigma x. And this has a beautiful name. This is called risk-adjusted return, right? There's your return, which is really an expected return, and this is a risk adjustment, meaning that they're subtracting from the expected return something that penalizes risk. And that's the idea. And by the way, gamma has a beautiful name in this case. Gamma is called the risk aversion parameter. And you turn it to get different portfolios. And if you turn it very low, if gamma is a small number, you will end up with something that has very high return and probably high risk as well. And if gamma gets really big, you'll end up in this problem. Basically, it's putting concentrating your portfolio in low risk investments or something like that. So this is the idea.